Thank you very much for doing this with us. We really appreciate it. This is an oral history interview with Ken Thompson. It's March 15th, 2024. We're in Sea Ranch, California, and I'm David Brock. So Ken, you were born in 1943 in New Orleans?
Yes.
Yeah. Could you tell us a little bit about just your family background?
My father was a military Navy pilot, and he was in flight training. This was right, in the beginning of the war, and he was in flight training to become, a fighter pilot. And we were stationed in New Orleans for just a little while. Flight training kind of thing. And I was born. Then we moved on. So New Orleans is not exactly my hometown.
Right.
It was 2 months there.
Well, I was just asking you a little bit about your mom and her background.
She was basically just a military housewife. It's a very hard job. You move and especially if your dad is on ships, on carriers, then she has to really move all by herself, drag 3 kids along. It was and then 2 years every place. She never settled down, never had a home.
Was that the rhythm of your guys moving from post to post?
Yes.
2 years?
2 years, yes.
2-3 years, yeah.
We were sometimes as short as 6 months, sometimes as long as 3 years, but that was the range. 2 is average.
And you were living abroad for some of those times?
Yes, I was 4th and 5th grades in Tokyo and Yokohama, respectively, and I was in 9th, 10th, and 11th grades in Naples, Italy.
And were you what was your sort of, before getting to high school, so what was your education sort of like in those moves? Would you go to a school on a base, or
no,
how did it work?
The bases were overseas. We went on schools over base, but we'd just go into the local community public school. It was very strange because I'm not sure you realize exactly how different public schools are in different pieces of the country. Like I would go, I don't want to pick on any particular state, but let's call Texas. I moved from California to Texas for 2 years and learned nothing, absolutely nothing. The only new thing that I got was Texas history and Spanish. That was it. And then I moved to a very good school military school in Naples, Italy, where I was 2-3 years behind. But it was exciting. It was exceptional. I had a older sister who was a homebody, and every move was the death. It was disastrous beyond, and she'd cry about it for months before we actually moved, and then she'd come home and say, "Janie's mom will take me. You just leave me here. I'll." and then when she'd move, she'd be in a funk until she found a couple of girlfriends, and so that was every 2 years. And my brother was the opposite. I was in the middle. My brother was the opposite of me. He was I guess a bully, a bad boy kind of guy. And he was with the police. He was always on his 8th life when we moved. And he got to start over, some other place. So he was ready to go. So that's the bringing up.
How just about your siblings? How did their lives unfold? Just be interested to hear.
My brother, being a brute and a bully, became a cop, and he went into the military.
Okay.
Was a paratrooper in Germany, and then was a surveyor for the city of San Diego, and then a cop for San Diego. And my sister, almost nothing. She just drifted and went around. She was at home. She got married like 3 or 4 or 5 times, and back and forth. She just drifted. She had no profession or goal.
One thing that I learned about in preparing for the interview was one thing that came up was how much contract bridge was an activity, I think, of your parents, if I got the story right.
Yeah, my parents were very big in bridge, very big, and my sister got it. The whole family had to play, but I quit very early, like in high school. I'd be drug off to these contract bridge tournament local things, right? And to me, it was, you could see marriages just crashing, where they'd yell and scream at each other and throw things, and it wasn't a friendly game. Contract bridge is not fun for me. And so I quit. Towards my senior year in college, I used to go down to the local lounge or whatever in the dorm or whatever and play, mainly just to pick up girls, and I'd just play stupid. I wouldn't remember the card. I'd purposely not remember cards and things like that. But it was social, and it was much more fun then.
And what were, sometimes households will have like a big theme in them, like politics or religion or art or learning. Do you think there was a theme like that kind of in your household?
No, except moving. Being a military family. As far as religion goes, my mother said we had to have religion. My dad had none, and my mother would enroll us in the nearest. It doesn't matter what denomination. It was non-denominational in that sense, but the nearest church. And then again in Texas, I remember that I went to the Calvary Baptist Church. If you know, kind of the screaming and the fainting and the speaking in tongues, and it was. I enjoyed it. It was a real show. I mean, it was impressive. And then I made a contract with my mom that if I read the Bible, I'd be exempt. And I read the Bible and I was exempt. And so that was the end of my church, right around 8th grade.
Okay. Thinking about, again, this period kind of before high school, were you, just thinking about sort of the activities that you were into as a youth, were you a big reader? Were you into tinkering? What sorts of things were you doing?
Well, again, I moved every 2 years, so I would build up a hobby, but then the hobby wouldn't move with me. It'd be too much or too big or too whatever. And so I had really eras of hobby every time we moved. God, let me think of the grades. In 7th grade, there was a vacant lot next door, and I built forts in there. Dug big holes and stole lumber, and they were massive, and they were all connected by telephones and were wired with lights and solenoids for the doors and things like that. So before that, in Japan, I started the electricity stuff and radios, built radios, repaired radios. That was 5th and 6th grade, kind of. Mm-hmm. Fourth, 5th, and 6th. did telephones. We were in a housing area, and the housing area had a barbed wire fence around it, and the fence was held up by wooden posts, wooden as opposed to steel. And I took the two top barbed wires and used them as a telephone line to my friend's house. And I had to jump. There was like two gates that were never used.
Okay.
But I had to jump those because there were discontinuities. But we used to talk over this this telephone system. That's such a fancy word for what it was. And but it power lines ran maybe 10 feet above these wires, and so it was totally drowned out by 50 cycles instead of 60, and you had to yell and yell and yell, but we did it. We yelled. So that, and then when I went to when I went to Italy, I built a robot and was into more electronics and audio. I had a huge audio collection, records, tape recorders, phonographs, things like that. Then when I came back to the States, my senior year in high school, I was in San Diego. And I started building hot rod cars.
Okay.
And I built a 40 Ford hot rod with a 52 Oldsmobile in it, and never got over that. And then in college, there was work, and I in the first 2 years of college it was double E.
Yeah.
Was strict, math, science, no variation at all. And then when I was a junior, the first time you actually broke out into double E, I got into computers, and I was in solid computers from basically junior through graduate school. I escaped. I went into work-study program, which is where you go to school for 6 months and then you work for 6 months.
Mm-hmm.
And I worked at a missile factory in San Diego, and went night school for basically non-technical subjects at night in San Diego State. And then at real school, I was at Berkeley, and I went for 1 semester and 1 summer session at Berkeley. And I didn't take the non-technical courses there because Berkeley's a pretty, intelligent school, and you have to go into these non-technical areas and they on the curve, and they just eat you alive.
Oh.
So I took them in San Diego State where they were pretty easy. I was at Berkeley when basically the free speech movement,
Yeah.
and the tear gas and all the good stuff. It was exciting time. It was really nice.
Could I take you back into more of your youth? And I just want to ask you a little bit more about some of these projects you were doing. Like, where were you getting sort of the know-how and the resources, the materials to kind of do all this stuff?
Mostly just reading.
Okay.
I took Popular Electronics, which I don't think it exists anymore, but it was a magazine. I didn't read it. I consumed it. I mean, I just lived with it, and I built about half of the things that they had. The robot was basically a frame for all the junk I had. I'd put all the radios in it, and I'd put the turntables in it, and I spotlights. It ran off of my dad would bring home airplane junk,
Mm-hmm.
and that I might use or might want, and there was spare aluminum for patching airplanes and things like that, and the siding was all aluminum. motor was a windshield wiper motor for an airplane, and like that. And every time they tended to remodel the airplanes once every couple of years. And if they rewired the airplanes, there'd be like more than a mile of wire that would come out of the airplane that they'd put back in, and
Right.
it was just thrown away. So I'd get a mile of airplane wire and build stuff with it, like telephone wires and things like that, and wire up everything.
Was the library an important resource for you?
No.
Okay.
There were no really good libraries I would read the typical first book, like the first chemical book or the first physics book, or in the library. But no, there was no follow-on after that. Do you know what the ARRL is? ARRL, American Radio Relay League.
It's a ham radio.
It's ham radio.
Yeah.
It's the ham radio thing, and they had a yearly paperback textbook. I don't know, not textbook, but book, which was called the Handbook, the American Radio Relay Handbook, and it was called the Bible. And I would take it and consume it from around 7th grade on, and that's probably where I got my double E background. I floated through double E in college because it was all second to me.
Right.
And that's where I if there was any continuing thing, it was the handbook, the Bible, or it was popular electronics.
Okay. And I'm sorry, were you about this? And could you talk? There were two things that I read about in other interviews with you or accounts about you, and one was about how it was, I think, in middle school that you first really got engaged with chess, which would become a lifelong interest of yours.
I remember it was 7th grade,
Mm-hmm.
and Bobby Fischer just won the U.S. Open Championship. Was on the front cover of Time or Look or one of the big display magazines that are around, and everyone was talking about Bobby Fischer, and so I thought I learned chess with at home and then went into chess. Actually, I learned it 2 or 3 years before that, and my brother and sister and my parents were I'd make them play until I won. So they'd throw games at me, right? Otherwise they'd have to stay there forever. So I knew the moves and I knew chess about then, but then as a study, it wasn't until the very first Fischer era. Fischer's the same age as I.
Okay.
And he's I don't know. He's on the front page of Look or Time or Life or something. My parents would go every Saturday night to a local hotel for a weekly contract bridge tournament, and I would sometimes play with them, but not often. But I would go, and in the lobby there were a bunch of old men, old, probably 50 years old. Look at me now. Playing chess, and I'd line up and take turns and play chess with them. So that's when I got serious enough to actually read a book about chess. And then I joined the chess club in school, in middle school. And just because I read a book, I think it wasn't talent, but just because I read a book, I was the top chess player in the thing. It's that. They learn the moves and they go and play chess and they get it's slaughter. So but then I actually started disliking the game. I loved the game as the game, but I didn't like playing chess, and I pretty much quit playing chess then for till now. But I treat it as a spectator sport, and I watch the games. I track them. I know who everybody is, and I went into computer chess, and I was always friends with top chess players. I mean, really the top, like the world champion and these kind of people. So anyway, that's my chess career.
Well, I wanted to ask you a little bit about something that I read too, that I think it was around the same age that, that you became really interested in binary arithmetic.
Oh no, being real interested is not the right word. I got a little calculator where you'd stick a pencil in a set of holes, 10 holes, decimal, and you'd run it up to add, and if it carried, you'd hook over and run down to add one to the next. So you'd do this, and it was a little tiny adding machine in a metal case. And I got to thinking about why is it 10? And I learned quickly it's 10 because of this. Right? And why couldn't it be 5? So I did 5, and then I did 4, 3, and then 1, I did 1. So I was into binary arithmetic, and on one occasion, just one occasion, it wasn't a deal, I actually did homework in binary.
Okay.
And because it's a lot easier to, the times tables are a lot smaller.
Well, when did computers come into your consciousness? Was that through popular electronics, or?
To some extent.
Yeah.
The hint of computers was around. I built, through electronics, I built some analog computers. And an analog computer is nothing but an op-amp. An op-amp is an amplifier with infinite gain. And with it, you can do wonderful things, just marvelous things. You can add, subtract, multiply, can't divide. But you can do functions, and you can do, with feedback, different kinds of feedback. And they are the heart of analog computers. And so I was into that probably in high school.
Okay.
And then I would build electronic things. I built there's a game called NIM that is, you put a pile of, you put any number of piles of matches, let's say, on the table. And your turn is you take some number of matches, any number, you can't skip, you got to take some, from any pile, throw them away, right? And then my turn is to do that. And then the winner is the one who's forced to take the last match.
Okay.
And that's, if you look at that game in binary, and you take the binary number of matches in each pile and line them up, you're in a winning position if there's an even number in each column.
Okay.
And it's a losing position if there's an odd number in each column. So if you're in a winning position and they're all even, anything you take away from any column will put it odd. One of the columns, the one column you pick, will turn odd.
Right.
And all you have to do is make it even. Okay. And then so you win. You just plain flat win. It's one of these wonderful games. And again, that's binary, and it's probably from the earlier playing around with binary. I built I was in a hotel living, waiting to move into housing in one of those moves, and there was a set of girls across the hotel and I'd wave to them, and it's like that. And so I thought, well, I'd like to build a signal box of some sort. And so I designed and half built, I didn't have enough time, we moved, a array of light bulbs where you could, with just a very few switches, you could put a letter up on the light bulbs, right? For this purpose, again, girls, and again that was design. There was another game I did called. It's like Fox and Crow, but it's a little bit more complicated. It's called Jealous Husbands, And it's the same thing. There's a river, and two sides. You got to get everybody across. And there's 3 couples, right? You got to get across. And the idea is that every husband is jealous of his wife if she's on the far side of the creek with the other men, no matter if their wives are there or not.
Okay.
And so I read about Quine McCluskey. It's Boolean algebra.
Okay.
And I was able to implement this in 6 double throw switches, these big knife switches, right?
Okay.
And so you line them up all at the bottom, and then it becomes a circuit if it's one of the husbands is jealous. So you just connect it to a buzzer. So you go like this, and again that was again getting into computers are based on Quine McCluskey, and the design of not software but the design of the real computers is based on that. So I got into that early, and then I was a ham radio guy for a while.
Okay.
I got my let's step back a second. I got my license taken away from me. I was working out of a NATO base. Naples had a neighboring town, Bagnoli, and in Bagnoli there was a big NATO base. And on the NATO base there was a set of clubs and things like that. Mm-hmm. There was a ham radio club, and they had great equipment, just great equipment. So I'd go there and play ham radio at night, right, on their equipment, on their call sign, and without a license. And the guy finally says, you got to get a license. So I got a license. It was mail away. He took the test and proctored and then mailed it away, and then I got my license. And then maybe a year later, there was a neighboring ham radio guy who had just a dirty set that would just splatter all over the band, right? Did you know what I mean?
Yeah, it would just interfere with everybody else.
And we tried to run away from him because he just made it impossible to communicate. It was really dirty, really. And so we actually chased him down and talked to him and said, I lied. I said I'm an double NG, an electrical engineer, and I'll clean up your radio for you. Just give me your radio in a month, and I'll fix it for you. Anything gets you off the radio. and he got mad at me and said no. And finally, and I probably shouldn't have, I turned him into the Italian. It's the PUC, the Public Utilities. It's the equivalent of the FCC, or they handle that stuff. And he got his license taken away for a month or 2 months or something like that. And so maybe 6 months after that, a new friend moved in from Paris, transferred from Paris to Naples, and had a girlfriend in Paris. And I told him, well, I can connect you up. If I can find a ham radio operator near Paris, I'll bring you into the NATO base, and the ham radio will bring the girl in, and you guys can talk all night, right? And sure enough, we set it up, and he talked all night. Now, unfortunately, that breaks all the laws in Europe. That you can only say, how are you, my singles, 5x9, that things. That's all you can give as a ham operator. It's called second-class messages.
Okay.
You can't, no first-class messages. You can't. And, of course, this was a 4-hour conversation of first-class messages, right? Because it competed with the phone company.
Right. Okay.
And the phone company ran the FCC or whatever you call it. So anyway, then I got a letter saying that from Italy, saying I couldn't, I'm kicked off, and they said that they'd sent the letter to the U.S. And then I got a letter from the U.S. saying I lost my license.
How did they ever catch it?
Oh, you got to give all the information when you talk and you say who you are.
Okay. So somebody
and I went over to
overheard.
this guy, and the guy who did it was the guy with the dirty radio.
Oh, okay. Yeah. Vendetta.
Yeah.
Yeah.
He got me back. It's okay. I shouldn't have done it.
Yeah.
It was my fault.
Well, I wondered, it sounds like you pursued your interests very intensely. I mean, does that sound right to you? Like, would you really dive into something and
Yes,
go with it?
I'd have a goal, something.
Yeah.
I wanted ham radio operators. I do it until I got it, right? Or I wanted to learn Morse code. I built a little buzzer and a keypad. God, I love semi-automatic keypads. They're just great. And I do it until I knew it, right? And on and on. It was. But yeah, but I was single-minded. I rarely had two interests at a time.
Well, could we? So how did things progress? Sort of by the end of high school. You were doing all these projects. Were you doing well in your classwork, or were you more focused on your projects? Or
No, I was very good in high school. Non-technical subjects, I got poor. So I got like a B average, where it was A's in technical and C's or D's in non-technical. and then when I went to college, it was a lot harder. At least the general part, the freshman, sophomore, math, science, that kind of stuff. And I was busy doing other stuff. And I got absolute C point. First semester I was on probation. I got lower than a C average. And part of it was because Berkeley in those days was a land grant school, and ROTC was required for freshmen and sophomore. And so I got F's in ROTC. Basically, they make you parade around with a rifle and dress up with a tie. I never had a tie before, and you couldn't just dismiss it. You couldn't just say, "Well, hell with it," because they could kick you out of school. They had the power to kick you out of school. But if you tried and failed, that's okay. And so I tried just enough to fail, and I got 3 semesters of F's in ROTC. I didn't do well in chemistry because there was an 8 o'clock lab, 5, and I got D in chemistry, and that brought me below C average. And in those days, below C average was probation, and another probation was out of school, and out of school was meant Vietnam. And so I learned halfway. Again, I was in work study, so I was only doing 6 months at a time. It was going to be 5 years to go through a 4-year college.
Right.
And after 2 full years, but only a year and a half of college, I discovered something in school that was wonderful, just marvelous. It's called a petition. And you go and get a petition, blank piece of paper, right? And it says, who are you? That kind of stuff. A couple of things, and what do you want? And you fill it out. It's like and you say, I want this. And you send it in, and they say yes or no. And it's the way to violate the rules of the school. And it's great. I mean, it's just great. They say you can only have so many units, or you can't take less than this, or you can't do more than that, or you have to take ROTC. And so I said that I flunked ROTC 3 times, and I said my petition was, and I was very careful, that I want to become a junior after 2 full years, even though I don't have the requirements for junior, because I only have a year and a half of college. And send it in. They said yes. I said, okay, no more ROTC. But then I was able to float my curriculum and do things. And then I used the petition probably half a dozen times after that to do.
To just shape things how you wanted to.
To do this, to do that, to do, yeah. It was a great discovery. I mean, everyone should know about petitions.
Well, could you describe how, how you really, your relationship with computers changed during those years, and you really became intensely interested in them?
In junior, there was a massive double E course, 5 units, labs, monster labs, everything about everything, and as soon as that happened in junior year, I sort of floated because I knew electronics pretty well. But the first thing they gave you was an analog computer course, and I did really great in that and then they had a computer, a G15, that one of the old double E's actually built it for Bendix Corporation, who was there, I went in, and I loved it, So I'd go back at night. I mean, it was unused except for class right now, and it was a worthless computer. It was very old. It was a drum computer, and I just programmed it and programmed it and programmed it, and then I got to know the professors, like including the engineer who actually designed it, and I slowly found all the computers on campus. I got a job in the computer center. I worked as an RA and a TA for a graduate student getting a PhD in computing. And I did all of his programming for him. And that was on a variety of machines. So slowly I built up where I had the key or the combination to every computer on campus. And even the big, massive central computer for the whole campus was only an 8 till 12 midnight on. No, they didn't have any staff or anything after that. But in those days, you don't turn machines off because you generate more electrical problems turning them on and off than you do keeping them on.
Right.
And so I had the ability, permission to come in at midnight and run it as my personal computer until 8 in the morning. This thing was like a full floor of a campus, and then I worked in the computer center. I did contract computing for the computer center for their apps, what you call apps now, not then. I had to sit in a little glass booth and find out what's wrong with somebody, physicists, Fortran program and that kind of stuff. I was good at that, really good at that, and. So anyway, that basically it was all computers after that first G15.
Can you talk about what it was that really grabbed you about it? It's kind of an unfair question, but get at some of what you were.
I can hint at it. I can't tell you because it's an addiction. You ask somebody what cocaine's like, and. I always had some problem I wanted to solve that was out of my ability because of computation, because of repetitive. And I'd find a computer and do it on it, and sometimes these things would last months, but I had months, and I had a whole variety of computers from, ThinkAS to massive. So I was into games too, and I had one of the teachers was Bell Labs. That was my Bell Labs connection. Was back from Bell Labs, and he was mostly in math, but it didn't matter. And he probably is the foremost game kind of guy. And
what's his name?
Elwin Burleycamp.
Okay.
He wrote a pair of books. It might be 3, but it's called Winning Ways. And it's part 1, part 2, and maybe part 3. I can't remember if there's 3 versions. And it's all about games and mathematical analysis of games and that. And a lot of that mathematical analysis is computerizable. And so I did a lot of work on games. And he'd treat me like an equal, and it was kind of cool because I'd get the big computer at midnight if I wanted it, and I'd write some game, and ask him to play it because he's the best player of any game. You pick the game and he's better at it. To come down and play my computer, and so he'd show up in sandals and a t-shirt and shorts at 12 at night to play my computer on my game on my computer, and so there was a lot of that. I had some goal, like some game or some combinatorial problem or some one of the big ones I did was pentominoes. Pentomino is if you take 5 squares, put them together so they hang together, like ... L, that's an L, or a T, ... So there's, and there are, oh my God, I can't even, there's 60 times, the sum of them is 60 squares, all of the different ones. So 60 divided by 5 is 20?
60 divided by 5. Yeah, it's not 20, it's 12.
12. There are 12 pentominoes. 12 different shapes of pentominoes.
Okay.
And you can count them reversed or forward. You can turn them upside down, around, you rotate them anyway. And the idea was to make a solid object out of the pentominoes. Mm-hmm. And there's 2 kind of cluster versions. One's a 10 by 6 solid, and one is 8 by 8 with a 2 by 2 hole in the middle. Mm-hmm. Those are the 2 closest to kind of mathematically pure. And so I wrote a program that would try all combinations of those and solve all of the pentomino problems. And I had there's several hundred, many hundreds of solutions, and I had them all on computer paper. Mm-hmm. And I had a little home set of pentominoes, and people would come over and try to do it. And then when you look it up, then you'd look it up on the thing, and you write your name on the solution. Anyway, my wife had her name in most of it, So that's the kind of thing, and it wasn't computers per se, other than they were fun to program, and they did what they were told. I mean, they were, anybody who came up to me in my role as finding people's bugs. Yeah. They would always blame the computer. The first shot was, this worked yesterday and now it doesn't work. And I said, well, what'd you change? Oh, I changed one thing, and you look at the one thing and it's right there. Yeah. So that they just worked. I mean, they there was no ambiguity. They worked. They did what they were supposed to do exactly. That was kind of I don't know, addictive. And then having them do that, the programming I loved, to do a job that was, and somehow an abstraction away from ands and ors and ones and zeros was also very fun.
They must have, there must have been a lot of trust involved for them to let you, use the main computer of the computer center at night. Did they, Well, I at that time I was actually, I was in the computer center. Okay. And there was some trust to do that. It's easy to kill these machines. But I certainly knew how to operate it, and I knew how to program it, and I knew how to lock and unlock the door. Well, let me just check out my question list real quick here. So while you were doing all that, so your undergraduate coursework, you were finishing around 1965, is that right? Somewhere in there?
65 was, yes.
Okay.
I graduated, with the class and commencement exercise, and the parents came up in '65. But I was one non-tech away from actual degree, and so in the middle of in the summer I took that degree. So in the middle of the summer I actually got the degree, but the signature says '65. June '65.
Were at that time, I think that Project Genie was already
Yes,
going on.
I was a year with Genie, and that's one of the computers I used a lot.
Okay.
And I knew Lamson and Littleiter. He was the professor involved with all this.
I think it was it Pirtle who was the...
Pirtle was fine, but he was less so than the...
Oh, well, Licklider funded it. Yeah.
Yeah.
Right.
Pirtle and Lamson and who's the guy with...
Peter Deutsch?
Deutsch, yes. I knew all of them. Deutsch was an amazing programmer, and I stole a ton of stuff later on from him. The ED syntax format, a lot of stuff. I stole it from Deutsch. Deutsch was good.
Could you talk about that? Were they their own kind of little scene in Berkeley computing, the Project Genie, or were they kind of
you make it sound
with
like Berkeley
people?
computing was a big deal. They were Berkeley computing, all five of them.
Okay, yeah.
and I was just going around having fun, and I was probably their only user outside of themselves.
Okay.
Their only external user, and I'd come in and complain about something, and it'd be fixed instantly because I had 5 to 1.
Oh yeah.
But I do it for my own kind of stuff. I wasn't doing it for I read all the code and I knew how everything worked there, but I don't think I did any programming on Genie per se. I think I just used it as a user.
Okay.
And it's just one of the dozen computers that I knew how to use.
Well, one of the things I was interested to ask you about was, I think it was Peter Deutsch who really was, as Butler Lamson tells it, Peter Deutsch wrote the QED editor, and then Butler Lamson helped write it up, and that's why, their names are both on the paper. But I mean, could you talk about how, you became influenced by that editor and for creating your own?
Well, I wasn't interested in editors. For the PDP-11, which was a really clumsy little machine, it was monstrously small. I needed an editor. And so I just stole the basic syntax of Deutsch's QED. But before that, I made 2 big improvements on it. One was, instead of searches, I did regular expressions. Mm-hmm. And then I added the global command, which says, for every regular expression, execute this normal command.
Ah.
And that's where the word grep came from. Global, regular expression, print.
Well,
which is exactly the syntax of the ED editor.
I wanted to ask you about that work, of kind of bringing in regular expressions.
I had a visiting professor for 1 year, Brzezowski, I think that's his name, and he was into finite state machines. He lived, breathed, he was. If he's still alive, I apologize, but it was a horrible class. But because it was too deep in one too narrow subject, right? But part of it was regular expressions, which are finite state machines. Which were regular algebra. Regular means something, and it's basically you can do anything with in computing and circuitry and anything like that if you don't count. It can't count, right? Like you can't have balanced parentheses. You can't recognize balanced parentheses because you got to know how many out to match the one in. Do you understand? So he had a a method of finding the finite state machine from some of his kind of stuff that he was using, right? And it sunk in, but I ignored it. And then when I got, I did contract programming for the humanities in school, and there was a professor named Oakes, AUCS, Oakes, who was into Dante. The liberal arts network of all the universities in the world divide up authors so that they're not spread all over. You can go to one place to pick on one author. They would divide them up by university. And Berkeley had Dante and I think Samuel Clemens, but I'm not positive about it because I didn't work on that. And Oakes was the head of Dante. And he wanted to do analysis, computer analysis of Dante, how many verbs and junk like that. And so I had a computer readable version of Dante, Paradise Lost, and I do funny things. And I started building the searches that he wanted done to find the answers he wanted with regular expressions. And so I adapted clean enclosure, which is another form of writing irregular expressions, which is the form that you probably know as regular expression. Clean enclosure expressions that I would convert into machine code through Brzezowski's reduction to finite state machines to go through Paradise Lost and change the word God to frog, everywhere, and things like that. And so that's where I started. It was strictly a job.
Okay.
And then when I got out of college and I needed an editor, sort of all those pieces kind of fell into place to do the editing, to get a good editor. I actually wrote a predecessor, which was an expanded version. It was actually functionally complete. It was a computer called QED.
Right.
Stealing again. On the Mac, Project Mac, MIT, CTSS.
Okay.
And when I first went to Bell Labs, my job and why I was hired was to work on Multics.
Right.
And Multics was being programmed by MIT, but the programming was done remotely on CTSS. And the editor there was just horrible. It was a line editor where you'd make a pass, and you go back to the top, and you make another pass. You can only go forward. You're going to go back. And so I wrote QED, which is a vastly superior editor from Deutsch, and added regular expressions. And I don't know, but then the space that you were working at wasn't like one piece of text. It was multiple spaces.
Okay.
You could edit this and edit this and edit this. And one of those spaces, any one of those spaces, you could set up as editing commands, because editing commands were just things you type. They're just text.
Right.
And so you could execute one from another, like macros.
So using the regular expressions, you can...
Well, no, using, you just say, the spaces had names. Let's call them A, B, and C, D, E, F, blah, blah, blah. You could have your text in A, what you're doing, really doing.
Yep.
And then your program in B, and then you can say run B.
Oh, wow.
And it's just text.
Sure.
And then that would edit by, mechanical repetition of whatever you wanted done. And B could call C, and C could call D, and you could do these recursively. So it was actually functionally complete, meaning Turing complete. It was a computer.
Wow.
You could do theoretically, you could do anything. And not me, but other people did it to add, subtract, multiply, and divide, where you have text as some number and you can convert it into another number by adding two numbers. There was one that would do it was the big mathematical thing before Rubik's. It was I forget. It was some game.
To solve some puzzle using
Some
QED.
puzzle, yes, using
Wow.
QED, and of course tic tac toe and all the kind of normal stuff.
So was this? I mean, for
And
people
it sort of took over CTSS.
that editor.
That editor took over the CTSS, and it became the heart of the Multics editor.
Okay. For people who aren't well, for me and for other people who aren't super familiar with regular expressions, it's almost like is it wrong to think of it as sort of like a form of almost like an equation that describes patterns in text? Or
If you read about it, they say what it is an expression that would generate massive numbers of, all the things that it would represent. It would represent, like if you say A, it would represent A, that's all. If you say A star, meaning any number of A's, it will represent nothing, A, and you build these expressions up. A or B would give you an A or a B.
okay.
A star B would give you an A, would give you a B, an AB, an AAB, AAAB. You see, on
Yes.
and on like that. So it would generate is the notion in the literature of what these finite state machines would do. But there's no difference between generating and recognizing. And so that if you have just a massive amount of stuff, some of it which could be generated and some couldn't, it would go through and select just the stuff that could be generated. And it was a fairly concise, easy statement of an expression you wanted to see. It begins with an A and ends with a Z. Like one of Kernighan's famous things is we had a dictionary, right?
Mm-hmm.
And he was asked to give all the words that could be printed on a calculator upside down.
Okay.
Do you know what I mean?
Yeah, I do.
Where 6 is,
Yeah.
And so what you do is you just you take all the letters, and if you want 5-letter words, you'd say an A or a B or a 9 or a 8 or a C or followed by another one 5 times. Just run that through, and in a fraction of a second, the dictionary, it would give you all the words that could be dirty words in on the calculator upside down, like goof or something.
Right.
So it would do that. That's what it is.
But this was a new use of regular expressions.
Yes, they were hidden away. They were around for quite a while. I really don't know the history of them. Their embodiment as finite state machines was definitely the hardware world but their embodiment of regular expressions, the earliest I know is clean enclosure kind of stuff.
Mm-hmm.
But it's certainly the first introduction into computing for
Right.
searches.
And well, I don't want to jump ahead, but maybe I will jump ahead just to keep with regular expressions. Once you did that work on Multics with QED, it also, I think that was your first patent.
Yes. It was a funny patent because the patent office now they weren't equipped to handle software patents. I mean, they just weren't equipped at all, and so they took the attitude that software patents couldn't be patented. They weren't legit, and mathematically, mentally, there's no difference between a hardware patent and a software patent.
Right.
Basically, you could build hardware to do this.
Right.
And so, in fact, the regular expression search algorithm was written up as a patent as a hardware device to search regular expressions. And then one of the claims, which is what you really say about it, is that it can be done in different forms, like computers, right? Down at the bottom of the computer, And it was granted, and I think, but I'm not positive, it certainly is one of the first, but I think it was the first software patent because it was hidden in a hardware patent.
Was that something that you were pushing the labs to patent, or did somebody
No.
realize this?
You don't understand the labs
I
at
guess
all.
not. Sorry, I thought I did.
The labs' one and only and major product is patents.
Right.
They run on patents.
Right.
And they live in the Bell system with the telephone companies and all of that stuff off their ability to write unencumbered code, by patents, right? So they had the largest corpus of patents, I think, in the world, certainly in the United States.
Wow.
And they would do what was called cross-license agreements.
Okay, sure.
Where you can use all our patents and we use all of your patents if you pay us $1,000 a year, right? And because we have more than you, and they just count patent to patent. And so the idea was to generate a patent. It wasn't like the patent that was you're going to change the world. It wasn't. It was a patent. It was 1, 2, 3 patent.
Yeah.
And so all of the they did recognize some patents were kind of special, like transistor, little tiny guys, but mostly they every MTS, that's the title everybody got hired at, and pretty much every MTS had a visit at least once a year, maybe twice, depending on how active they were. What have you done lately? Can we patent it?
Okay.
And they had a whole patent department, and you say, yeah, that, and then some guy would come out and delve into it, and if he liked it, it would become a patent, not by you, by Bell Labs.
Sure.
And that's what happened with the regular expression algorithm patent. And the guy was just versed. He was really good. I've had a lot of patents. I had a patent that was that was good. I thought it was a good patent, right? And when it was part of Unix. And Unix was sold. They couldn't. It was given away. It was. I'll call it sold, but selling something was against the charter of Bell Labs, right? So it wasn't exactly sold, but it was sold for some like a few $100s to universities. But there was a pending patent on something integral to Unix, and in it was a thing saying, and you have to do patent fees, because that's what they were really in for, if this patent ever delivers. And so there was about 50 Unixes out when the patent was delivered. And they came, and rather than going out and collecting $50 patent fee, some number, I don't know, $20, something, patent fee 50 times from the guys even chasing them down. They didn't want to do that. They put it in the public domain.
Wow.
And just kissed it off.
Wow.
And at that point, I just became cynical. And so every time the patent guy came out, the phrase in the patent legislature is, a patent is something that's not novel to anybody skilled in the art. That's
Right.
the wording.
Right.
And so anytime he came out and he says, what you doing? I'm not doing anything not novel, nothing novel that's by anybody in skilled in the art. And so I stopped patents from then on.
Oh, really?
I quit.
What was
Because
that?
it was a waste of time, and it was just a bit counter. Now I'm co-author on a lot of patents from other people who were the major patent holder, right? But I have many more patents, but none on my own.
Okay. To kind of go back, if I could, I wanted to ask you to go back to kind of this, Deutsch and Lamson making QED, you doing your QED with regular expressions. It's it has struck me how many highly prominent people in computing have worked on editors and made editors.
It's like the editor, computer 101. Rob Pike did a QED like editor, but it was very good. The Emacs guys and it's true.
I was just wondering if I can't. I'm
It's
curious
personal.
why.
It's personal. Everybody I know who did it use it, right? I mean, they type it and you do it. There's a personality involved, like if you're verbose and know how to type, you have long words and things like that. You know what I mean? And so usually what you can go around and find the parts that you like, personal again, you like from different editors, from different things, from different ideas, and you put them together and that's your editor. And you do that because you want it. It's your tool.
Okay.
And it's because you use it. It's not because editors are fun to start with. It's because you're building something that you would use personally day by day.
I get it. Right, and you have the skills and capacity to make it.
Yeah.
So why wouldn't you make the perfect editor for you?
Yes.
Okay. Thank you. Well, I wanted to talk about that visiting professor from Bell Labs who came to Berkeley.
Burley Camp.
Who, he seemed to have been really helpful to you in sort of, your graduate school time and then in the recruitment to Bell Labs. Could you talk about that?
The first thing that he did he'd show up at midnight in the computer center, right? And he'd talk about anything, anybody. He was just open. He had office hours, but just because he was supposed to write something on the card outside his room, but mostly he was just, ready to talk to anybody for anything. And games, I was into games and he was into games. I got a game story, but I'll tell the game story. I wrote a game called, not sure it had a name at those days, but it's become crosses and hatches. Basically, there's a computer screen of an array of dots.
Mm-hmm.
And one side wants to connect the left edge with the right edge, and the other guy wants to connect north to south, right? And so you take a turn, you connect one notch, right? And he was unbeatable. I'd come back with 10 versions of this thing, and he was just totally unbeatable. When in fact, so I cheated once, and basically it was 20 by 20 to start with. I made it 19 by 20. and it's on these horrible, 80-year-old screens now, that are round, that are CRT screens that are, and so they're all bent out of shape, the lines go like this.
Right.
Anyway, so it's really hard to catch a subtle thing like that. And I started beating him, and it just warmed my heart. So anyway,
did he ever catch it?
I told him. I don't know whether he caught it or not, but in the end, he knew.
But he really must have. I mean, he really must have been impressed by you to, I heard that he was the person who just basically signed you up for graduate school, and
he did. I wasn't interested in graduate school, and he just signed me up. He had an early class, and I would very often sleep in it, and he'd throw racers at me, and the very first test, which was some programming and some computer design and stuff, basically everything I really knew, I got an absolute 100 on it, and he says, I don't give 100, and he knocked it off for penmanship or spelling or something, and gave me a 99. So anyway, and we talk a lot about lots of things. And then I went back to Berkeley to teach for a year. And he was the head of the department and brought me back.
Okay.
And we'd make jokes because the professors in these departments are characters. They're just special. Every one of them is special in a very special way. And we'd make bets before these meetings, that so and so will complain about that. Or this one will say no, and this one will say yes, and then one of us would win in the middle of this meeting and flip the other one a quarter across the room. So anyway, he was a very good friend, and then he came back to Bell Labs.
Okay.
I can't remember whether it was a year before me or no, it had to be. He came back the same time I did, and then only stayed a few years, and then went back to Berkeley and became a joint professor of math and computer science, and ran the math center up on the hill.
Okay. And he was also the person who was responsible in connecting you with the Bell Labs recruiter who had of Berkeley as their territory, if you will.
Yes,
okay.
And the recruiter just chased me down like a dog.
And you were, again, not particularly interested in...
I wasn't interested, no. In fact, I was actually negative because the idea of working for a phone company, Jesus, who would want to do that? Climbing telephone poles and, and I didn't quite realize that BTL was the patent center, the research center of the phone company. Mm. And it wasn't until I actually recruited. That's how little I knew about it or what and I started recognizing all the names in all the papers at the place, like the inventor of the FFT and, little things like that,
And during that recruitment process, did they know which group they wanted you to join, or was that part of the discussion?
The way the recruiting works is that the recruiter sends back, this is so-and-so X, and that's distributed to everybody who has openings. And they all bid and say, yeah, we'd like to see him. And so I got like 5 or 6 openings, and then when I go, then there's a second decision. I have to pick them, and they have to pick me because then there's the actual person-to-person interview there, and if they don't like me for their job application, then they say no, and I don't get an offer from them. And then if they get multiple offers, then I will get those offers and select or reject them. So that's the way it works. And so I got like 6 interview offers, and most of them, you got a picture of the time of the industry, the ecological time.
We're 66 now.
66, yes. There are a lot of hardware people, and they were building things in hardware, and suddenly computers come along, and they don't know anything about computers, and they want some computer application to design a piece of hardware or to find out how many coils it was a computer assistance to hardware.
Yep.
And I thought that was the most boring thing in the world. So I said no to all those. Some of those places were great and interesting. Like there was the ABM project. ABM is the anti-ballistic missiles.
The Nike Zeus stuff and all of that. Yes. Amazing.
And they were working on that and doing the computing for it. And it was kind of funny because my work study, I worked in a missile plant in San Diego where they built the Atlas. And they take the Atlas up to Vandenberg Air Force Base and shoot it at Kwajalein. And at Kwajalein, there was Bell Labs trying to shoot it down. Okay? And then they drag all of the data from the attempt to the labs and analyze it there. And one of the places I went was where they get the data and try to do the software and the merging and the firing of this bug-eye radar. The heart of it was a bug-eye radar, a phased array radar. And And what they had was a tape drive, if I can call it that. There was approximately, a reel was around 7 feet in diameter.
Oh my gosh.
Not diameter, in diameter. And it was about this wide and would travel at 60 miles an hour through the heads. And that would be the real response from the radar.
Okay.
And then they would test that and try to get, anyway, whatever they did, right? And so I'd walk into one of these places and they'd want something, something basically that I wasn't interested in. And I'd say, yeah, I know this is recruitment, but I'm here against my will. and I want to know what you're doing. And they just light up and they tell them all this stuff about this 60-mile-an-hour tape drive. I get to see everything, and it was fun. It turned out to be a lot of fun by just saying no, really quick no. And a later no, I think would piss them off, but an early no was great. And so there were only two places that I felt comfortable. One was the place I took, and one was a very similar place. And both at Murray Hill. These other ones were at Whippany and Homedale. I didn't go to Homedale. And the ones that were attached to military, I had a infant aversion to military. So anyway, that was the recruiting process.
So did Doug McElroy was he interviewing with you for?
No, he didn't interview me. I was interviewed by Shin Lin, who's a mathematician, and Carl Christensen, who was a computer guy. He actually did he dealt with computers like I did. There were only two people that I interviewed at each of these places. McElroy was in the math department, which hadn't quite merged with computer yet.
Okay.
And so, I mean, things changed from the time I interviewed and said yes and the time I went. I interviewed in fall or late summer of my graduate year.
Yep.
And then I went in June of my graduate year.
I guess another way of putting the question is, did you know that you were going to come and be working on Multics?
I'll be honest, I can't remember.
Mm-hmm.
I don't think so. I don't think Multics was really built out when I did it. But
Okay.
I knew before I went that that's what I was going to be doing.
Operating systems?
Operating systems, Multics, yes.
Okay. And could you just talk a little bit about the aspects of Multics that you liked, the aspects of it that you didn't like, as a project?
Oh, as a project.
Or as a goal.
It was horrible as a project. It was split among three groups that fought each other. Not fisticuffs, but there was lots of political push and pull between the three groups. It was mainly controlled by MIT, which was coming off of a brilliant success with CTSS. It was probably, for its date, it was by far the best time-sharing system in the world. And they said, well, now we're going to do one better. And that's the death of now we can do anything we want. We got the money before we start, and it doesn't have to be simple. It doesn't have to work. We can over design it. We can do anything, and that's Multics. It involved 3 or 4 brand new concepts, each of which somehow interacted with others to make it hugely complicated, very, very hard. And it was so hard that a normal computer, a normal, like the Genie 940 computer couldn't do. And they had the third component, Bell Labs MIT, and the computer manufacturer had to be part of it, and they built the computer for it.
Mm-hmm.
And it was big and slow and ugly and very expensive because you had to buy a computer with it, a special computer with it. And it was just destined to be dead before it started. It was a birth as a, I don't know, a platypus.
I understood that it had like a whole shelf of paper for as like the user manual or something.
Yeah, it was the user manual, the MSPM, the Multics System Programming Manual.
Yes.
And it was 8 feet wide, on a shelf, and it was, I don't know, it was so over designed, it was beyond belief, and Bell Labs was into it. The word they used was a computer utility.
Mm-hmm.
Like you plug into the wall, and it's like electrical utility. This is a computer utility. Whenever you wanted, you do it. And if you wanted more, you got more. And, everybody could get full machine or on and on. So it was oversold and too complicated to be built. Over time, way over the budget, way over everything. And I lost interest in it almost always. I was tasked to do things for it, on it. I did. They were good. They fit the cog.
Mm-hmm.
They had a design cog, and I fit it perfectly. But I had no interest in it, and never used it. It was horrible to use, and pretty soon Bell Labs figured it out.
And so you were on that for maybe 2-3 years or something, or
it could be, but that the truth was I was on it for 6 months while I read the 8 feet of manual, and after that I did what I was told, but mostly I did what I wanted to do.
Right. I wondered if you had worked at all with Dennis Ritchie on Multics. Were you collaborating with him? Were you collaborating with anybody else?
In those days, Dennis was not as much as I into Multics. He was working with Andy Hall and Altran.
Okay.
It's a Fortran-like language where instead of playing with numbers, you were playing with formula, with formulas and things.
Okay.
It was quite successful and quite well done. And Dennis did much of the groundbreaking work on it. And I think he was a little bit into Multics, but not that much.
Okay. Well, I wondered if you could briefly share, I guess, what seemed like what you described as a really great way to get to know people at Bell Labs, which was keeping a baby alligator in your office.
Basically, some friends of mine, unknown to me, sent me an alligator from Florida, and it showed up in the mail, in a box, little tube, and said alligator. And I assume that's just what they wrote to make you open it. And I opened it, and it was an alligator. And I worked much more than I was at home. I was at work probably at least 2/3 of my time. Barely enough to sleep, at home. And so I kept the alligator at work and fed it. Loved it, even though it was nothing but they're not the best, sweetest of pets. I don't know if you know this or not.
Yeah, I can imagine.
They have no loyalty at all, and I'd feed it the cheapest fish I could find. It was tripe. I remember it was tripe. I've never had tripe, never ate tripe. I've never heard of tripe until I went to the to the meat department and said, I want the cheapest, and they gave it to me. I guess it's bait or something. I don't know what it is, but anyway, my alligator loved it, and I bought 50 pounds of it. I bought a lot of it for like 50 cents, and would feed it to him, throw it in his dish, and he'd snap it up, and then he lasted most of the summer. I got him right after I got to Bell Labs. I mean, like days after I got to Bell Labs, and he lived, thrived. I mean, he just loved it. He had his little pool, and people were feeding him all the time. And it's great. So he got out, and I looked for him, and I looked for him, and I looked for him. Couldn't find him. I spent probably a week, large fraction of a week, searching for him. Looking for. And towards the end of the week, I was basically searching for his dead carcass because they can't live without water very long. And then I gave up. And shortly after I gave up, he showed up in a secretary's office and had the secretaries just completely scared. I mean, they were screaming. I mean, really screaming. And one of them was quite literally on the desk, on top of the desk, yelling. And I came in, and from the commotion, I kind of knew what it was. I had a hint, and grabbed it and ran back and threw it in the water. The water was still there, and then everybody, slowly but surely, everybody at Bell Labs heard about it and came through my office, and it was fun. They all came in. They all got bit. Anything that came over the edge of the thing was called tripe. And it was getting close to dangerous.
Yeah.
If it had lived another few months, it would have been dangerous. But it was about that long. And then so I got to meet everybody, and I knew departments and what departments did, and I could get math help, I could get electronics help, I could get chemistry help, I could get materials help, and boy, I mean, some of the people I met during those few days when everybody came by my office was, I knew and were friends with for dozens of years.
Well, I want to ask you about, it seems like humor is something that's very kind of important to you, or something that you value. Is that right?
I don't know. I think it's too much. So I'm a practical jokester of some sort, and some of the things I've done, I look back on and say I shouldn't have done that. That was wrong, and so I try to back off. But yeah, I like to have fun. Things are fun. I don't mind being the butt of jokes, but also I don't mind making other people the butt of jokes. So I figure it's even.
Well, I wanted to talk about the moment when Bell Labs kind of quit Multics, and what that meant for you personally. I mean, it sounds like you have been kind of distancing yourself a little bit from the effort beforehand, but did the fact that Multics was now dead at Bell Labs, did that have a lot of consequence for you?
It had a lot of consequence. Well, it's several dimensions. One is the computer became completely available. This one-of-a-kind monster computer that, and I actually took it over and started programming it for a while. Was one consequence. I was free. I had no work to do. That was, I was on my own. Another thing was that I wanted to do an operating systems to fit me, personal, and not to build an operating system for other people, but to build it for me, like the editor discussion we had. I wanted my operating system, and none of the operating systems I knew. And in those days, operating systems came with a computer, and everyone was different.
Right.
And everyone was, by and large, horrible. They I don't know. They couldn't let you do your work, and now suddenly I can now work on the operating system, but Bell Labs, I actually got reprimands saying don't work on operating systems. Bell Labs is out of operating systems. This was a bad experience. We spent a ton of money on it, and we got nothing out of it. It's no good. Operating systems are a bad subject. And I don't know. So I started working on the Multics computer. It's called a GE645.
Right.
Their main computer was a GE635, and this was modified to be the Multics computer. And it was just idle. It was just sitting there. It was ours, And so I took advantage. But it was on its way out. They were told them to get rid of it, but it took 6 months to get it out of the door. So I was working on it, and I actually had it. It was hugely complicated. The interconnections. It had separate computers to do everything. Separate drum computer. Oh, the peripherals on it were great. Oh my God, the peripherals! It had a set of disks that were faster than anything I could even imagine. It had a thing called a CRAM, C-R-A-M.
Yeah,
and what it was a thing about the size of a pool table, and it had film. It was rectangular, about this big, and it had notches on the side, and the notches were binary address.
Okay.
They were they were either notched or not notched down about 10 slots, and these film were lined up in the middle of the pool table and just stacked one on another, and the notches were on the bottom. And there was a set of aluminum rods underneath and come up on the notches with a code. See? And if all the notches matched, one card stuck up. So it would select one card out of all the cards. And then there was a racetrack. There were two drum heads, one at each end of the pool table. And it would pull it out one way or the other. And there was a circular track of generator hoses. And it would catch in the hose and then go down, race down, and then wrap around the track, wrap around the head, and become the surface of the head. And it was fun for me because it was a type of programming I loved. You could actually, while you're reading this one on the head, you could drag another one out and start it on the way. Plus, you could have one going out the other way, going out the other head, right? And so you could, while one's coming up, you could be unloading the one coming back, and it would just stick it on the end. It was, so it was a marvelous. I mean, it was an amazing device and had zillions, of bits of memory. And totally unreliable. It just it would explode. And there'd be these head things, but it was fun. And so I was playing with that and getting it to work. And the very fast drum. But it had an I/O machine which was as big as the computer. First off, it was a multiprocessor. I think it was 3 or 4 processors out of shared memory, which sort of almost didn't exist in those days. And it had a separate processor that had the same interface as the 3 or 4 processors, which is called a GIOC, the General Input Output Controller.
Okay.
And you do all your input through that. And that was a separate computer that used the central processor's access to memory to get its stuff. And it ran all the teletypes and all the peripherals, the cram, and all those things. And I finally conquered it. It was a bitch, you know. And I finally conquered it. And I could program it, and I got the teletypes all running. It actually, all the teletypes came up and said hello, you know.
So forgive me if I'm being a little bit slow, but because was it running Multics, or were you writing your own system?
I was writing raw code right at the very bottom level.
Okay, just like, okay. Yeah. But you were bringing up services on it. So you...
No, the services are very hard, large, you know, big... Much, I could say hello on a teletype.
Okay.
If that's a service, then I was doing services.
Okay.
and I was playing with some of the tapes and the cram. I love the cram. You know, it was the cram was made by the French. GE was in bed with a French company called Boule.
Okay, yeah, sure.
And I think this was a Boule device. But anyway. It was fun but worthless. I don't know. That's my life. That's my whole being. And just about the time I was ready to start writing programs to read and write the teletypes to actually run programs is when it went out the door.
Okay.
With me hanging on to it, yelling and screaming. And that's when I ran off and found the PDP-11 that was totally unused.
And that had been part of this graphics 2 system, right?
Yes.
From Bill Ninke?
Yes.
Yeah.
Yes.
But was he still in Murray Hill then, or
I
had
think
he
so.
left?
I think
okay.
so. I mostly talked about with some other guy, and I can't remember his name. I can't remember. The guy I talked to mostly, who had done all the programming for it.
Okay.
Is the one I talked to, and he's the one that had the old manuals lying around that I could Xerox his manuals and use them. I'd never seen a PDP-11 before.
And so this is quite a step down in terms of capabilities of a machine
monstrous.
Different class entirely, right?
Oh, it's about 3 classes.
Okay.
Oh, you have no idea. I have no idea.
Yeah.
One would fill this house.
Yeah.
And one would be one corner of that room.
Okay. Yeah. And so, one question I had is like, why, you were looking for a machine that you could have total control over, right? Because you wanted to...
Well, my first, you make it sound like I plan things. I don't.
Okay.
And my initial goal, what I was really interested in, was the kind of algorithm that you need for the cram. That and it had a really high-speed drum, and I wanted to write drum-seeking algorithms. I wanted to get throughput on drums, because drums, in the computer center sense and in Multics sense, and everybody I ever knew couldn't deal with drums well.
Okay.
They would disks and drums. Basically, they would say read and wait for the read to come back. What you want to do is simultaneous overlapped reads. And you had to know where they're rotating, what head to use, where each head was.
Right.
And it's like the cram. You got to know what's on each head and what's coming down the pike. And,
right.
It's the kind of programming I just thrived over. It's the kind of programming you do for DSPs, where you ask to load something and it'll come up in like 4 cycles, but you got those 4 cycles to make room for it, and things like that.
Yeah.
So that was my goal, is to write a very good disk scheduling algorithm. And that's what I did on the PDP-7. That was the first goal, first thing.
Sort of continue work on that particular
Yes.
effort. Yeah.
Yeah, because I thought it was interesting and useful, There were a bunch of scheduling algorithms in the literature, but in my opinion, they all had flaws, really serious flaws. Like if you really tried very hard to minimize, the things. If somebody wanted 1, 2, 3, 4, 5, 6, 7, he'd get the whole machine. Everybody else would wait, because that's the for throughput on the drum. He's the guy.
Right.
He lined them up. He knew every, and so those kind of the flaws that were fundamental. That you want to be fair. Also, not only there were users' considerations as well as drum considerations.
Right.
And so anyway, I actually got that running. That was pretty good, and it became the focus of the file system for Unix, or at least the disk part of the file system for Unix. And then I had to write programs to test. I mean,
Right.
Having a disk just sit there and you say, "Well, that's a nice disk." And you got to read and you got to write, and then that's not good, because every disk can read and write, right? What you want to do is have multiple simultaneous reads and writes to tune your algorithm.
Right.
And so you have to have these test programs lying around, and that means you have to load them up, run them, and run. And suddenly, without knowing it, I mean, this was sneaking up on me. I had no idea. I was really behind the times. Suddenly, it's an operating system. All it needed was a text editor and a multiplexing layer to you run him for a while, run him for a while, run him for a while.
Right.
And that's it. It had a file system, it had a disk driver, it had I/O peripherals, it had, it had everything except the ability to maintain itself. So I needed a compiler, editor, an assembler, a loader, and user protection to run multiple users. And those were very small parts compared to what was already there, just to drive the disk.
So you suddenly realized, I'm actually, a substantial way toward this other interest that I had of making an operating system for me, my operating system.
Now, I don't know whether my myopia was real, or whether I was just avoiding telling Bell Labs that I was doing something I was told explicitly not to do.
Right.
It's one or the other. I don't know which.
Yeah. Okay. And then you also had an opportunity to really go for it, to fill out to create these other pieces that you needed, because your family was going on a trip or something.
My wife was going to visit my parents. My parents were in San Diego, and we with the new baby were in New Jersey. So I shipped her out with the baby to. Two things were happening at that point. Fisher was playing for the World Championship in Reykjavik, and I needed time to write my 3 programs to get it, turn it into an operating system, a real utility.
Well, I mean, I guess the way that you describe it right now, it's just sort of, one thing leading to the next thing, leading to the next thing in a way. But I wanted to ask you, but it does seem that there is kind of like a design intention, or that there was a design, sensibility going into, what you were making when you were finishing this operating system, that...
I had an idea of what I wanted, but it wasn't... Like you said, I don't think I ever designed any one big thing. I snuck up on it in different ways.
Well, could you talk about, I guess what I'm, kind of threshing around trying to get to is like, what were the key elements of what, your operating system was going to be like versus, these other ones?
It was going to be interactive, fast, as far as, it's a slow machine. If you had asked to do a big job, you couldn't get it done because the machine couldn't do it. But if you asked for a little job, it would be instantaneous. And a little job is editing and assembling, and compiling and loading. And it would compile itself in right around 10 or 15 seconds. So anyway, it was meant to be where you weren't waiting on the computer. That was the whole idea. What I wanted to do was program games, whatever, lots of things. I had lots of things on the fire, but what I wanted to do is do those and not wait for the computer. Wouldn't want to wait overnight for a tape to be punched. I didn't want to, you know what I mean. Some of the things were, serious delays if you wanted special stuff. The GE 635, which became the major computer at Bell Laboratories after the 45 was dumped, they were sort of forced to have a time-sharing option where they would take and dump simultaneous jobs in memory, but just run the same old, horrible. Basically, it was like you're submitting batch jobs.
Yeah,
from your
virtual
terminal.
batch processing or something.
Yeah, it was pretty gross. And
well, was also, it seems in listening to you that part of for your operating system, part of it too was, the self-sustaining. I can't remember the exact phrase you used, but part of the point was you could change the system yourself. That it was, if you wanted to do something new, you could just.
Well, yeah. Well, yeah. I don't think that was a goal.
Okay.
It was certainly. I don't design whole things at a time. I kind of design the least thing that I want next to be done for some reason, and therefore it has to be adaptable. That's part of the original design, is that it has to expand. But yeah, I don't.
And in this work that you were doing on the algorithm for the disk and for testing it and then onto the rest of the operating system, you were programming this in your own assembly language?
No, I was programming it. That's part of the reason why I needed an assembler.
Oh.
To make it an operating system. That was
get
one
it.
of the last steps. The way to program that machine was to run a PDP-11 assembler on the 635.
And then bring it back.
And they would punch paper tape. You bring the paper tape back and load it in through the tape reader.
Of course. Okay.
And all of this, I think the goal behind all of this was to get something as smooth, not as powerful. That's not the word. That's not a good word. It's usually a pejorative term, but a smooth, like CTSS or Genie.
Okay. Well, after you did this incredible 3-week push to get these pieces together, when did you start showing it to other people?
They came around. I was Dennis came around. Dennis was working on space travel with me during this time on the same machine, and knew the machine code. Doug came in later and did a compiler on it. Really good job. And that led to writing compilers in the compiler. Before that was an all assembly language. And let me think who else. Bob Morris came around to do some funny floating point kind of stuff, multiple precision arithmetic and things like that. Let me think who else. That might have been pretty much our users community. Brian was there, but I don't think he he never used it much. Pretty sure he had a user ID, but all the user IDs were 1 digit. That definitely put a limit on.
And did it? I know at one. I heard one time you describe. You had a normal teleprinter, Model 33 attached to it. Now, did you also make a kind of a glass teletype sort of a thing?
Yes, that was first. In fact, it came before the. That's where I did most of the programming for turning it into an operating system. Was on the glass teletype was my Model 33 rather than Model 33 because I was. We adopted ASCII very early, and Model 33 is Baudot. It's all lowercase. It's a 5-bit code, and ASCII is a 7 or 8-bit code depending on which version of it you read at what time. And so we adopted ASCII almost instantly, and that's because it's superior, and it was clear it was going to come, and it was the Multics code. So we had a full character set for ASCII on the screen.
Okay.
And a keyboard that one of the there was a department that they did lots of very nice hardware kind of work for things, and they built keyboards, really nice, like typewriter professional keyboards.
Right.
And they were trying out some, and I got one that on the screen side.
Okay. Because I was wondering if it already had one when it was used as Graphic 2.
I don't remember, to be honest.
Yeah, I know on Graphic 1 they had a keyboard right there by the scope, but I don't know about.
They probably did.
Yeah,
Maybe they did.
But you wrote that. To make it the
yes
the display writer or whatever you want to call it. Yeah.
It was a very funny thing. It was a vector graphics thing, where you could draw a line from A to B. That was the opcode. So you had to make these.
Well, when did the effort to create a high-level language for the system come in?
Okay, the sequence was that Doug built TMG, which was a compiler, recursive descent compiler. It would parse compiler kind of syntax and issue things every time it found something, right? And he wrote the compiler, and he wrote the compiler in the compiler. So it was self-contained.
Wow.
Self-containing thing. It was a masterful job. It was amazing. It was great. And I wrote B in that language. And then I wrote B in B because it was that kind of language. And then Dennis wanted to use B on the 635. It only existed on the 7. And he moved it with a compiler. He actually produced code, while my B only produced opcode stuff. An internal language, an intermediate language that I interpreted to actually get things done.
Okay.
And part of that was because of space. There was no space on the PDP-7. and it had to compile itself, which was just horrible in 4K. And so he was moving to the 635, which is infinite space, right? And so he actually wrote a real compiler for the 635 and called that thing NB, newbie.
Mm-hmm.
And then life went on. Then we got our PDP-11. And he was working on the 635 on B and making things. And we got our PDP-11. And the PDP-11 was a byte machine instead of a word machine. And B is pure words.
Mm.
I mean, it doesn't like bytes at all. It really does not like bytes. So he modified for the PDP-11 the B language to handle bytes efficiently. And it was very well done. And it was installing types. Now, B had no types. There was no type. And the reason is because they were all words.
Okay.
And so the operator told you what to do with 2 words. You know, you could look it up as an indirect. It's a pointer. You could add 2 of them. They were integers or floating points. You could, so the operator told you what to do with words. And B had no types, nothing but words. That's why it was so painful on a PDP-11, because you had to combine 4 bytes to make a word.
Mm.
And if you really wanted only a byte worth of data in it, you're wasting 3/4 of precious space.
Got it.
So he added types to newbie and added basically one of the types is byte to newbie. And when that happened, it was time to move Unix over to a PDP-11, and that's the animal. The first version was written in PDP-11 assembly language.
Okay.
And then Dennis and I decided to write it in newbie or whatever I don't think we really called it, And so I was writing it in the current version of newbie, and I just lost track. It was just too big and complicated. Things fell off the floor, and I couldn't pick it up, and certain things were too hard to do. And then so I'd go back and we have a discussion, Dennis and I, and we'd come up with a modification to newbie, put it in, I'd try again. Now the third version of Unix on the PDP-11 in a higher level language is the one that worked. And it was when Dennis put structures in newbie, and then we had to name it. It was called C. And so Dennis wrote, call it in C now, the whole version. He wrote C on the 635. He brought it over to the PDP-11. He modified it to be operating system sensitive until it was able to support an operating system well enough to, and somewhere along there it's changed its name to C.
That's it's so interesting how the two efforts are so interacting and reciprocal, and again, like in listening to you describe it, it's just iterating, trying things, building from one thing to the next, like you say. But again, I'm just wondering, were there, but you are, working hard to create this new high-level language. Were there things about the language that were things that, you and Dennis Ritchie both really liked? Was this another chance?
Well, everything we did was moving off the problems with B. B was never really an operating system language. It was used to write B, so it was a compiler language, especially if the compiler was word-oriented. And we used it to drive the typesetter and a couple of other things. because it was immensely portable. I could change the intermediate language in way less than a day and have a full running bee on any machine.
Okay.
And so it was so portable. And so when we get a random ratchet machine that, like the types that are like the general data, I forget what it's called, for the typesetter. The typesetter ran off of a general purpose machine. I put B on it and used it because we handle typesetting very differently than Mergenthaler, who sold the machine.
And were there any other elements of C that really reflected, things that you both wanted?
Types he put in. Mm-hmm. And then structures eventually came. It was the last thing to come in. And it was necessary to kind of structure the data systems you need for a big thing like an operating system. No, it just got better every time, and almost everything we did was to take some piece of B out of it and put something better in.
Okay.
And again, I say we consulted on what to do next and what was wrong with the current one. Dennis did the work.
Okay. It's just so fascinating to me that that both of these things developed in this fashion that you describe. Both Unix and C have proved to be, so enduring. When the context of their creation, seems so specific. I just wondered if have you thought about what has...
I think it was Bell Labs. I think it's the non-pressure, no users. They're not waiting for a product so they can sell it. It was essentially whatever you want to do, atmosphere, and for anybody you wanted to do it for, atmosphere. It was Bell Labs. It was by far the biggest contributor to this whole type of programming.
I was looking too that that this whole trajectory that we just sort of described from the summer of '69, I guess, through Unix written in C on the PDP-11 '73, summer of '73. That's just 4 years.
Yeah.
And this is a time when you were like from 26 years old to 30 or something like that. I just wondered, how that period of time felt to you. Did it feel, different from other time periods? Did it feel like incredibly productive, or?
It was productive in a higher level sense, but the same kind of intricacy. The same thing I did in playing with games and things like that in Berkeley. It was always the same. I'd go to sleep worrying about something, and then wake up, yes, and I'd run off to the computer center and do it, kind of thing. But it was step by step with no pressure, no problem, no problems. I didn't have to satisfy anybody. Mm-hmm. I built up a user community internally and then externally. That I get feedback from, and I'd weigh it and say yes or no. It wasn't a demand. It was just a suggestion, right? And it was a good suggestion. I would steal it in a minute.
We talked a little bit earlier about grep. Was that? I guess that just related to, Ed had regular expressions in it, so this was a continuation of that.
there was a manual that I wrote on the PDP-11 for the editor, because people have to come in, they have to read something, right? And in it had a list of the commands, basically alphabetically. A means append, B means buffer, C means change, and on and on. And then when it got to G means grep, right? G, and it doesn't mean grep, it means generate, something like that. I can't even remember the word. And it says, for every regular expression, do this command. And then the command was the definition of the whole thing, A, B, C, D, E, G. And it said, for example, G/RE/P means for every regular expression, print.
Okay.
which is the name, and it was easy to pull that out. I actually had that as a private command for a very long time, until Doug asked me if I could do something like that, and I pulled it out. I gave it to him after that.
And let's see, how important was it to you and the effort that Doug McElroy became, such an early and enthusiastic user of the system?
He worked on his own things, but he had suggestions that were just penetrating, like grep, like pipes, like other things like that. But mainly he was working on his own. He did the speech synthesis.
Right.
He did all the map stuff, all the projections on maps and things like that. And he ran his own thing. But that doesn't mean he didn't slough off ideas to everybody. And he was the head of the department, and you have to have your head of your department sign any paper that goes out from the bottom, right? And so he knew every paper written in the whole place, and he not just read it; he understood it and studied it. He knew. I've never met anybody like it that could read a complex paper in subject A and a complex paper in subject B and give cogent, coherent critique on both, on either.
And on the language too, right? On
Yes.
just on the writing. I've heard,
he and Dennis were wordsmiths. They both were.
There were a couple other. We talked about some of the other Bell Labs researchers who were part of your early user community. There was one. Well, there were maybe a couple that we hadn't hit on that I wanted to ask about. Two, really. One is Lorinda Cherry.
Yes.
Could you talk about her and just her kind of place in the community?
I think because not overt, but definitely discrimination against women. She never quite, I think she was ultimately promoted to MTS, but mostly she was an assistant to Bob Morris.
Oh.
And Bob Morris, I think treated her like a full research assistant, a full, researcher, and had her do a ton of programming for him, and it wasn't just one way; it was mutual. So, I had very little I knew her well, but her office was right across the hall from mine, but I didn't have any close contact with her. But I knew all the work she was doing through Morris.
Okay.
And it was all really good work. Yeah.
I was just really intrigued by that project she worked on, I think, a little bit later on, called the Writer's Workbench.
Okay, that was the collection of randoms. I thought, maybe I don't know it well. I know what Writer's Workbench became known as, and it was, I thought it was out of an external, even home Dell department that put together a system called Writer's Workbench, which was a Unix system built around all the literary, editors and typesetters and spell correctors
Right.
and all that, as a single thing to do manuals or whatever you want to do and that kind of thing. And I know she did some of the early work in it, but putting it together under the term Writer's Workbench, I thought it was that external department.
Yeah, I'm not quite sure. I thought somehow that she was involved in kind of seeing it through into that, but
It could be. She could have been consulting with them
maybe that's
tremendously.
what it was.
It could have been. But they were in Piscataway, I guess. That's where they were.
Okay. And the other person is, I guess there's two other. Rudd Canaday, if I'm saying his
Rudd
last
Canaday.
name. Yeah.
Rudd Canaday was from Whippany.
Oh.
And I talked to him about the file system and how to make the file system. And we got together in an office that there was a new system at Bell Laboratories where you could call a telephone number and take dictation. And then the next day it would be typed and sent to your office, right? I mean, it would sound stupid now, but
Sounds great.
so anyway, Dennis, me, and Rudd got together in an office, and Dennis and I never heard of this new system, and Rudd typed the new system and said, "Wait a second," and typed the new system, and we designed the Unix operating system, the Unix file system on the blackboard, talking into the dictation, and it all came back. But it was like inode,
Oh, yeah.
The way it came back was special. It was, some of them were hilarious, to be honest. But anyway, it all came back, and then Rudd, I guess he always had religion, but he actually went and joined, became the church and left the labs before he was sucked into the the cyclone that was Unix.
And
so he's never part of it, but he was in some of the initial stuff.
And the other person I went to ask about is Joe Osana.
Oh wow, Joe was the I don't know how to describe him, but he was the doer. You go to him and say, "I want to teletype in my home. Something can't be done." He'd go off and do it. And that particular one, I want to teletype in my home. It required a Bell Labs OPX. It was very expensive to make a phone call. They'd charge you like 10 cents every 3 minutes. And if you're on all day, that's, $100 a day, right? I mean, and that's a real $100. That's different than today's $100. And so what we had Bell Labs extensions, wired through the phone company to Bell Labs from our homes.
Okay.
And we had teletypes delivered from Bell Lab Corporation in our home. And the way Joe did it is he wrote a couple of forms. I mean, he just invented it, teletype in the home, and addresses and approvals and shit like that. And then fill it out for us and send it in. And of course, somebody got it and said, "What is this?" "Oh, it's a teletype for the home." And he'd explain how to do it. Who you contacted teletype to get it done, and who you contacted the phone company to get the wire to your home, and it would get done. And he did that several times. He bought the typesetter. He bought the. He was the doer. He got us the rooms when we changed rooms and things. He got us the rooms. He dealt with things. You know what I mean? He got things done.
Well, one of the things that we haven't talked about yet, that I think Joe Osana was very involved with, was eventually the kind of cover story that turned into a real story about using Unix to do document preparation for the patent department. Was he involved with that?
He was certainly involved
Yeah.
with that. He was involved, period, and definitely with that. He was trying to get a PDP-11 for us, and we were being told no because we don't deal in operating systems. So if we don't deal with operating systems, we deal in word processing because Bell Labs makes patents,
Yeah.
which is nothing but word processing. And it's happened very fortuitously that the patent department had on loan a document preparing system from a random vendor that they were evaluating for use to buy. It was not bought yet. And probably Joe went over and said, "Hey, I got a deal for you." and so we got our first PDP-11. Money was never a problem. It was operating systems was the problem, right? So we got our first PDP-11 to do word processing. It was paid for by Max. It wasn't paid for by our department, by our area. And we had full-time users, 8 to 5 users, which were the secretaries for the patent department, writing patents on our system. And that grew into the ability to actually finally get our own system when it started becoming a very popular system. It first spread inside the Bell system. It was being used for the administrative kind of stuff, typing in trouble tickets. This line is broken, this
Right.
thing, and doing the correlation for these things to find out what piece of equipment was probably broken, and then it started actually doing some switching and stuff like that. It was getting deeper and deeper into the guts of the Bell system, and becoming very popular. And because of that, they couldn't deny it anymore that it was an operating system. It sort of took over. And
I wanted to ask.
and Joe, when the first typesetter came in, we had he wrote NROF, which was, there's an old program, ROF, that developed in many ways, but he wrote it so that it was actually macro driven. And you'd write a macro that would be invoked every time you got to the 21st line of a page, or you know what I mean? And in it, he could easily write a set of macros in this one language that would file patents, that would do patents. And that's what we gave their macro header for our runoff that Joe did, was what the patent secretaries used for patents during that period of time.
Right.
And then when the typesetter came in, he converted it to typesetting, but then he died. He had a heart attack and died. And Brian took over the typesetting, and adapted typesetting much more to mathematics, stuff like that, more computer sciencey kind of things.
Right.
But the basics, the bottom level, was Joe did that. That was sort of his one programming thing, as opposed to being a gopher. God, he was good at that.
I wondered why it was Max Matthews' group who bought the PDP-11.
Yes.
Was that they were just interested in seeing the work go forward?
They had extra money, and if
Oh.
they didn't spend it, they lose it next year.
Okay. Yeah.
They just bought it. It was year end.
Yeah.
There was a department head in Max who was I was grunt, MTS at the bottom, and my next level supervisor was called a department head, and his next level supervisor was called a director.
Right.
And Max was a director, and he had a department head in him named Lee McMahon, who was a very strange person, very great. I mean, good guy. And he, I think, was tasked with getting the computer for us. And then when we got the computer, he actually left that department and came over to our center. And he was a wordsmith. He was in early days he was a monk. He had about 3 or 4 PhDs. He would translate from ancient Arabic to something else in the catacombs of Rome. I mean, his life was amazing. He had a Austin Healey, big beautiful one, right? But no driver's license. And he'd clean it and polish it and tune it and everything. And then his wife would get in and drive him around. And he was amazing. He knew everything about everything religious. Like when the Dead Sea Scrolls came out, he knew what they were and all of the politics involved in them and everything. And just regaled us with stories about religion, but crossed with early literature. And he's the one that did all of the dictionary work we did. One of the first things he did was we got machine-readable version of the Federalist Papers, the first constitutional papers by all the framers. And about half of them are authored and about half of them are anonymous. And we did a whole bunch of parsing of sentence structure and use of vocabulary and things like that, and got big hits on all the anonymous ones. We knew exactly who did every one of them. And he did things like that. And he negotiated to get all our dictionaries. And there was a 1,000,000-word corpus, which is supposed to be a cross-section of the use of the English language called the Brown corpus.
Yes.
He got that and used it for everything, he was kind of the literature kind of guy and really good. I mean, in today's world, he would never even be hired. Do you understand? I mean, and Bell Labs was full of that. We had an astronomer. We had that had a slot in the South Pole every winter, and I mean, things like that wouldn't happen today. There's no place that would just deal with research. I only know of one place before that, and that was RCA, and one place contemporary, but they didn't match Bell Labs at all. That's IBM. IBM had a research center, but they were all driven by IBM.
Thank you. Well, I wanted to, actually my next question kind of plays off of that a little bit, which is just about eventually with I think the second PDP-11, that was kind of around the time, I believe, when the kind of Unix room formed, where people would...
Yeah, I think the first one didn't, but we actually got a spot on the 6th floor where we cleaned out a vending machine and a couple of cages of stored junk from 1920. And I think we had the first Unix machine there. I'm sure we had the PDP-11 for the patent people.
Okay.
Had there, definitely. But our own PDP-11 we finally got, and it was a modified PDP-1145 that had PDP-10 base limit register protection, because up until now, all the users could write over their other people users' space. Oh. Even the operating system. It was all in one space. And they came out with partitions in the PDP-11. It was a KS-11. KS means special system out of... and so we asked them to design it. They designed it. We iterated a couple times, and then they delivered it really fast. DEC used to be that way. They used to really make machines for you. and then we used that until the 1170 came along, that had it built into the original, had protection built in.
Well, I was just kind of interested in this, in the Unix room as kind of like a shared workspace, because I mean, I think everybody had their own office.
Right.
But it sounds like a lot of the time everybody would choose to work together at the terminals in this room.
Well, there were, yes, I think everybody did. They all had terminals in their office if they wanted them.
Mm-hmm.
They all had terminals at home if they wanted them. Joe Osana again. And but they kind of had they had terminals in the Unix room, and the Unix room was always, I don't know, it was a hotbed of things. You talked about the typesetter, what we're going to do, things like that. Lunchroom, the Unix lunch was also one. It was 1:15 because the lunchroom closed at 1:30, but they would take your order at 1:15, and so we'd all come in to that. It killed me to get up and be in at 1:15. And if I was late, I'd buy McDonald's and sit down at the lunchroom with my McDonald's. They used to get mad at me for that. But it's just part of the, I don't know, I don't know. It just caused a symbiosis of thought and things. It was great. That's where you learned about what somebody was thinking about that might turn into a project, like the typesetter, like the next computer we were going to build, or that kind of stuff. Networking, things like that.
Right. And I guess were you, it sounds like, would you have described yourself as kind of a workaholic at that time?
Yeah.
Yeah.
Absolutely.
And it seems like you were more working in the nighttime, or your schedule
Well,
was...
I would get up for the Unix room for the lunch, and then I'd work. I'd try to go home because we had a kid at that time. I'd try to go home for the kid, put him to bed, give him a bath, put him into bed, read a story, but then I'd go back to work. And sometimes when I go back to work, Bonnie has a story that I told her I was going to be home at 7, and she called me about 6 and said, "I thought you were going to be home at 7." And I said, "I am. I got an hour." It was the next 7.
Well, I guess I wanted to ask you, when it first became clear to you and other people, I guess, that like in the nature of Unix it seems like it made it particularly prone to it having variants and variations, because it was, because so many things could be added to it, so many tools and variations of tools and things like that. When did that start to become clear that there were
as soon as it was leased to most people took it the way it was. All the universities, they were all first. They took it the way it was. ARPA wanted to distribute the ARPANET and made a contract to Berkeley. And Berkeley made a version of it that was fortified. It was more stable. And it had the drivers for the ARPANET and the connections and the hardware.
Right.
And that the hardware is all maintained by BB&N. And so that was a version, right? And that was probably the first and only real version of ours. But then it started being not university sent, but freely sent. You could buy it. I don't know how that came back. It came in with part of the start of the dismantling of the Bell system.
Right.
We weren't allowed to sell it, And so companies that were, there was a new microprocessor that was faster, 5 times faster than the previous one, nearly every year. And every company started, like Sun and SGI, they all grabbed them together and put them together and made a computer out of it, but then they needed an operating system. So they would take Unix. And then, I don't know whether it was because they had users with a particular bent, like graphics for
Right.
SGI or whether they were trying to differentiate themselves from the other. But for some reason, they all took and modified the version. But it was, in my opinion, and it may be wrong, that it was just based on the fact that the hardware was in an exponential growth. It was just, it was unbelievable what was going on as the root size on VLSI was getting halved every year or so. These things that go by a factor of 4 in speed, and the next one just clobbered the previous one, even though it was a year later. And they all needed, a company would always would embrace one of these microprocessors and need software, and they always took Unix because it was portable.
I guess somewhat connected to that, there was something that Dennis Ritchie wrote about Unix one time where he said that a motivation for it was to create a system, and this phrase was, around which a fellowship could form. And I always thought that was a really interesting phrase, and it really seemed like that happened for research.
I think it's it's retrograde. I think he wrote about it because it happened.
Oh, because a fellowship formed that he wrote that. Yeah.
But I don't think it was ever a forward thought.
Yeah.
Oh, hey, I want to make a fellowship.
Okay.
It was almost the opposite.
Yeah.
I want to do something for me.
Yeah. Right.
And so it's good words, and he always put good words in things. But I wouldn't call it a forward reason.
Intention.
Yeah.
Well, what I was trying to do was I was trying to connect that idea to this other idea that a lot of people have drawn a direct line from the sort of open source software movement and ethos, and many people draw a line straight back to Unix, that's where it comes from. And I was just interested to get your take on how do you see a line there? And
I see a relationship, not a line.
Okay.
I think open source comes much more through MIT.
Mm-hmm.
And what's his name? Stallman?
Yep.
But Unix had a bit of that, and the part about a fellowship, a group of people, is that for some reason, and I think it's just because of me and Dennis, everything was open. We had protection on files. If you didn't want somebody to read it, you could set some bits, and then nobody could read them, right? But nobody set those permissions on anything. Anybody, all of the source was writable by anybody. It was just open, and if you had an idea for an editor, you pull the editor out, you'd write on it and put it back. And there was a mantra going around that you touch it, you own it, and that's exactly what it was. Is that if you go in and edited something, that was written in the file system that so and so edited it last. He owned it, right?
Okay.
And that means if you have a bitch about it, you'd go in and find the owner, and that was a variable name. But the fact that everybody's directories were readable completely, their files were mostly always readable, but quite often writable. You could go in and modify people's file, and and people snooped, and it wasn't a bad deal. It wasn't like peeping Tom looking in somebody's bedroom. It was people snooped and to find out what people were doing because we're a bunch of introverts up there. And for example, the first software tools book, Kernahan and Plogger.
Yes.
Plogger was a science fiction writer, and he was quite popular. There was a monthly science fiction magazine that he would put lots of things. He had a huge list of, he wrote a lot.
Okay.
And whatever he was writing on was in his directory, right? So we'd all go in there and be reading it as he's writing it, right? And we'd all write back, "Hey, you ought to kill this guy and move him over here and turn him green or something," and he didn't mind it because that's just the theory of Unix in those days. And I think that generated a fellowship. Just the fact that it was like writing on a blackboard, everybody read it.
Well, I would have come back to that idea in a minute, but I did want to ask you about your work on the number 5 ESS. Rob Pike, who I talked to a bit before coming to this interview, told me to ask you about... He
ratted me on it, huh?
Yeah, he ratted you out about the number 5 ESS. No, he said that was something that wasn't well known. And I went to... well, you mentioned Unix getting into switching, so...
Yes.
Yeah.
It's a long story, and I don't know how much of it. Number 5 was done at Indian Hill at Chicago. And they were into it, and they were pushing their own operating system. EPL was the code. It was horrible, and their own they for reliability they had rules, and the rules were just onerous. I mean, it was very strange, and it was a very strange system. Number 5 ESS. If you ever looked at it down the bit level, it's just weird. And the people in the workers in number 5 ESS were saying, we got to do this in C. This EPL stuff is no good. C kind of works. It's available. We can just use it. Everybody knows it. And they write EPL in C, right? I mean, EPL is written in C, and everybody knows it. So they had a showdown, right, where they were going to invite all the C people and Unix people from Murray Hill and contrast that with EPL people from there. And it was a political slime job. I mean, it really was. And first off, the EPL people got up there and they had a slide of the Unix worker with his bag of tricks, and on the side he's a little cartoon of a bag of tricks, and it was like that through the whole thing, And we got up there, and by the time they finished their thing, we just got up there and said, "This is how you do this. This is how you do that," and thought, well, we're just going to get slaughtered, This, we shouldn't even have come to this.
Yeah.
They were using it as an excuse to make a decision they already made, right? And so we went home and we found out that they're going to change to C. And but then Unix was more than number 5. There was a PBX division in Denver, and they were having trouble.
Mm-hmm.
So Joe Osana bought a if you can believe it, it's a multiprocessor analog bus, where someone would put a D to A on a wire, another one would A to D it off the wire, and they would share this thing. And on the wire was the phone conversations in little chunks, right?
Mm-hmm.
And you could add more the processors they call phone lines. They were just phone lines, right? and Joe Condon bought one, ripped out the computer, and put in a PDP-11 LSI-11.
Okay.
And we installed it in the Unix room. It was the phone system for the Unix room.
Okay.
And the original phone system in the Unix room, because everybody had an extension of their phones in the Unix room, there was like 50 buttons on this phone. It was a phone about this big and like 6 columns of buttons. It was not what it was meant to be. And it had a cable about this big going out onto the floor and going to everybody's office. So we replaced that with a 2-wire cable, basically it's just a plug-in phone, and we put a little speaker in it so it could talk to you. That was the ring, if you will, and connected it up to this PBX that was built with a Unix, and then we wrote switching software, and they'd come out with. We read their list of switching and what worked and all the restrictions and how many people you could put on a line, and it was all kind of weird, arbitrary restrictions and stuff. So we rewrote that with an idea, and had a PBX for the Unix room that would ring, and the ring was phone call for Ken. It would say that was the ring, right, for whoever it was for, and. It got to where it wasn't a ring anymore. You never heard it unless it said phone call. Phone call somehow tempered your mind to say who it was for, but you still wouldn't hear it until it said Ken, and you'd pick up the phone. So you never heard the rings. You only heard your ring, and after a while in here, and. That was a psychological thing I never knew, but it was definitely real. And then there was like 4 or 5 or 6 of these little tiny PBX things. They only had like one button on them, and you pick it up. And so if you pick it up, it was yours, but next time it would ring on the other phones, So there was only one simultaneous conversation on any phone, but you could pick it up from any phone, and you can't.
Got it.
And we put in all of the multi-user holds, callback, their whole list of things, and we added a whole bunch of really weird stuff too on top of it, and told them about it, and then they looked at our software really closely and took it back. This is PBX, not number 5. Number 5 took C from us, but
okay, and so both of those were huge businesses for the company, right? I mean,
yes, not 5 was and still is huge, but
they're still running today, right?
Yes. They're the ones who do the mobile stuff. But from a room full of 5, I mean, like a monster room, now it's a box about this big.
But was that a real kind of, was that another kind of extraordinary proof of Unix and C for the Bell system?
I don't know, not Unix and C. I think the biggest deal of that was the fact that it was electronic switching rather than mechanical switching, like these big PBX things. You pushed the button, basically connected your phone to one of the 50 lines that came in.
Right.
And this was doing electronic switching back in the first level PBX. And with that, suddenly the world opens. You don't have to deal with with anything. It just changed everything. And then you need a model of the phones. And our model was that there's this thing that produced voice, right? And you could connect any phone to it. And it would be a multi. If there were if there were two transmitters, they were together, right? And that's what a phone. So a phone call was two transmitters, two receivers.
Mm-hmm.
And so but if you say, I want to bring someone in, it'd be 3 in 1. Or if you have one guy talking to somebody with 5 people listening, you could do that.
Right.
So it was a very simple model. And all you had to do was implement that as an operating system primitive, connect a transmitter, connect a receiver.
Mm.
And I think that they did a huge amount of modification in the PBX too, but we didn't follow them. I mean, that wasn't our job.
Well, I wanted to switch gears just a little bit with this next question, which I guess goes back to Unix proper, which is, I guess in any time sharing system, security of a sort is a concern, making sure people don't mess up other people's stuff. And also, I guess, keeping people out of the system you don't want in there. And so I was just interested in, hearing you talk about, where your ideas started to form about, putting the Trojan horse in the compiler and how that whole thing started, and actually, trying it out on people. If you could talk a little bit, but how did that start?
I'd love to talk about this. All right. I got the idea, and it says so in the paper, that there was a security audit of Multics,
Mm-hmm.
which was supposed to be very secure. That was one of the hard things that they were doing. And talking about the whole idea of this Trojan horse, and it's sort of. And I said, hey, that's cool. I'll try it, And so I actually built, I wrote one in a day and put it into the system, and got one of the Unix support group people to track it, right, to get it, and then it went nowhere, and I didn't want it to go anywhere. So anyway, it was around, and I forgot about it, totally forgot about it for 10 years, right? And then I got the Turing Award, and I suddenly realized, oh, that's great, yeah. I'm going to have to give a paper and a talk. And so I said, what am I going to talk about? I have no idea what to talk about. I avoided papers, avoided anything like that. And so I got all the Turing Award papers previous to mine. Right? Mm. And I read them all. And I put them in little packets on the table, of what they were about. And one of them was, this is what I did to get my Turing Award, and a paper that he already wrote, because that's how he got his Turing Award, right? And then there was one, well, they're going to have to publish this anyway, so I'm going to talk about saving the whales.
Okay, yeah.
So there was a pack of saving the whales, or stopping apartheid, or something like that, right? And then there was one that I liked, was a MPU, minimum publishable unit. And what it was is that if you read this guy's history of his papers, he had a set of papers that were MPUs apart. Mm-hmm. You understand?
Mm-hmm.
And it's the minimum amount of work you can do on a previous paper to make it publishable again.
Okay.
And it was publish or perish in those days. It was really serious, right? All these associate professors going in and getting thrown out after 5 years. And so they typically only counted papers. They didn't count, progress.
Yeah.
And so there were a bunch of them that I considered, I called MPUs. There was an MPU paper. And what it was is I assumed that he missed MPU by a little bit, and he got rejected from a previous. Mm-hmm. So he pulled out his just sub MPU paper and gave it as a Turing Award. And then there was anyway, and there was a bunch of personal ones. This is how I became so important. I went to school and I did this and I did that and I did the other thing. So anyway, I had these 5 or 6 categories of papers, and I decided I really didn't want to do any of those. And so I actually, for months, I hemmed and hawed. I worried about it, right? And I didn't know what I was going to do, and it kept me up at night. It was really serious. Well, what am I going to give a talk on that's going to be published, no matter what I say? And Dennis, at the same time, wrote a drizzly paper. Have you read his?
Yes.
What did you think of it?
Well,
really stood up, didn't it, over time?
I mean, it was very brief.
No, Dennis was long and
His
boring.
Turing lecture?
Yeah.
No, I think it's almost as long as yours.
No, okay.
Oh, who knows? Maybe I read the wrong one. I read a very short one by him recently.
Okay, it was the history of the Bell system and how it got competed out of existence.
Okay.
And all of the logos and
I didn't see that.
Anyway, he would gather everybody together to practice this talk, and he'd practice it, right? And everyone said, "Oh, that's great," right? And they go away, and then he'd make some changes, and he'd gather everybody together to do it again. And this time only half of the people showed up, and then finally I was the only one to show up for like the 5th version of this paper. And I'm saying, I don't want to do this. I really don't want to do this. And definitely he was in one of these categories, right? And it was at a SIGOPS conference in Mount Washington in New Hampshire, that I said, what about this old thing that I did, years ago? That'd be a cool paper, and I'll give it as a joke, that no one would expect anything like this. And so I wrote it on slides. I didn't write it as a paper. I just wrote it on slides, and it was very, very quick that I had to actually give it at the ACM thing in New York. And so I took the slides and I just put them up and gave the talk. And it went over great, because half of the people didn't know what I was talking about, and half of the people just stood stunned. And then suddenly they go, "Oh!" I could feel the breath of the of the auditorium go in and out like this as they took their breath. And it went over great. And then I spent hours trying to explain it to journalists that came up that were just, go tell me what this guy was saying, and I spent hours and hours, Anyway, so I gave it. And then they said, okay, write a paper. I had no paper, right? And I hemmed and hawed about that. And I actually missed the deadline by a year. Our paper, because he put them together, came out a year after when it was supposed to. And that's because of me, because I really didn't want to write that down. I don't know why. It was just, and then so finally I wrote it. Now, before this talk, nobody had heard it. Nobody. And I was afraid that if I gave it out loud or practiced it in a crowd of more than one, that somebody would object to it, be upset. And and then finally, so I finally wrote the paper down to submit to the ACM, and gave it to Dennis and said, and he submitted them on both. And I had, as the title of the paper, the second half of the Turing Award lecture. That was the title of the thing. And Dennis had his as Reflections on Something, and he edited my title into Reflections on Trusting Trust. So that was not me at all. I didn't even know about it until it showed up in the ACM. And so anyway, and then it showed up, and then it started winning awards by itself. But it was a joke. It was a...
Well, it was very interesting for me when, even though it may have been a joke for you, it was very interesting for me when I read it, both because I think there was something for me very, interesting and profound in there about, the succession of compilers as a form of kind of learning, which I thought was a really interesting observation. But also, so there's that. But I also wanted to ask you about, when you actually tried it out within the Bell system, did people notice it? I mean, did people find it?
Something smelled. They found something wrong and were chasing it down and broke it. It was designed to break. If you tried to poke at it too hard. If you tried to find out what it was, it would turn itself off.
Oh, really?
Yeah. And they broke it by trying to find out what it was. And then it wasn't. And in the Pasadena talk, somebody asked me if about it.
Yeah.
And I said that funny thing about it, it's been 20 years, maybe even more. Yeah, it's more like 30 years.
Yeah.
No one's ever asked me for the code. Nobody's ever asked me for the code. I said, and then a good friend of mine, Russ Cox, I don't know if you know him or of him. Oh, you will. He's cool. He's good. Called me up and said, as soon as you said you had it, I want it. So I gave it to him, and he wrote a paper on. He put it on a one of these simulated PDP-11s. Did the whole thing, explained it, got it running, compiled the login command, got the login command debugged, and did it. And it's all online, and basically you.
Oh, I'll have to. Well, that was one of the questions that I had when I saw that you said that you had the code. My first thought was like, oh, well, maybe we could collect that for the Computer History Museum. But I also wondered, is that kind of an attack still
we actually
out there today?
Yes. At Google, one of the attacks on Google was attacked like that.
Really?
Yes.
Well, in the, I'm sorry.
I think it's a worthless attack, as a real honest to goodness attack, because, let me push that down for a second, except for, and I'll get to that, because it's so much easier to break into a system by calling up the operator and says, I'm your boss, what's the password? And they'll tell you. It just works. It's happened a dozen times, right? At every place I've worked, that somebody calls up and wants the password, right? So it's so weighed down on human effort to do this that I think it's pretty much worthless. Now, the place where it's not worthless, if you put it in a lower level, not in software, put it in hardware, like in IP router or in
a chip.
Or in a chip somewhere. But, I think it's very easy to do. And if you're a big distributor of a big IP router, if you're somebody like, I won't mention any names, it would be very hard to detect, virtually impossible, and it would infect everything. It would, and I wouldn't be a bit surprised if something like that is buried in different systems that have various amounts of popularity, vulnerability, and by popularity. But that's the only exception I can think where it'd be worth doing that. If you just want to break into somebody's system, you don't
call up.
Yeah, just call them up.
Well, in hardware, would you be able to have the same features of the attack that you describe in the paper?
Yes.
That it could reproduce itself?
Well, the reproduction you don't need, but you can. If the hardware was run by Microsoft microcode, which it normally is, then you can have reproduction code in the microcode, so it doesn't smell. It doesn't, and then you can ship the hardware and the microcode and all that microcode is maintained by the manufacturer, they don't allow anybody to do
Right.
random things on it. So it definitely would be easy to do in a router or something that has a ton of software or microcode in it, or like PBX or a number 5 ESS, or you know what I mean.
Yeah.
And as such, you could just snoop it. Whatever it has a domain, like if it's sending traffic back and forth, if it's just communication, it can snoop the communication and find something that it likes and record it and or ship off to another line. It's
Ship it off and rewrite the logs or something.
it wouldn't. It's the one that writes the logs, or
Right. Oh, okay. Yeah. Just don't put it in the log. Yeah.
yeah. So that kind of attack, I think, is really important for somebody. It has to be a manufacturer that produces something that everybody has or uses. Like routing software or
Phone
software, or
Well, I was really struck by one of the lines in that paper, which was, I think, your conclusion, where you said you can't trust code that you did not totally create yourself. And I just wondered do you still believe that?
to some extent. Again, it's not worth doing in some sense. Like I explained, it's much easier paths to go. And if you get caught at it, you're in deep trouble. Like Sony putting this index file on one of their CDs.
Oh, I don't know about that.
Oh. If you get caught at it, you can be run out of the business. I guess it's similar to what TikTok is going through right now. But I think you can, if you're at the right level, you virtually can't be taught until somebody inside spills the beans. But you really have to be in the right position. You have to almost dominate the industry in a particular element that you definitely control, because you maintain and do all versions of the software or hardware or microcode yourself, and don't allow other people to touch that stuff.
Mm-hmm.
And everything in the order of packet switching or routing or things you have lying around the house by the dozens. The things that really scare me, I have no idea why they exist or are popular. Things like Alexa, which is designed to be they scream to be attacked like this. Do you understand what I mean?
Mm-hmm.
They're just horrible devices to have sitting in your house, listening and interpreting all your Wi-Fi and interpreting all your voice, and a lot of them have cameras too. I mean, why would anybody put something like that in their house? It's totally controlled by another manufacturer, and a lot of those manufacturers have some pretty dismal histories.
Well, I was interested, like, how your interest in kind of security, was that something that really developed for you when you began working on Unix and after, or was that something that you were interested in before when you were in graduate school, or?
No, it was sort of near. It was between those two. For some reason, I don't know why, I was there was. Do you know what DES is? Digital encryption standard from
Yes.
the Standard Bureau of Standards. Well, the story behind that is very complex. It goes through IBM, NBS, and it was great in some sense that it created the open source cryptography community. Before that, there was nothing. I mean, there was, substitute an A for an I in the backs of these little magazines. And after that, they all came out of the woodwork and were trying to analyze DES because DES had some secrets in it. They had these so-called switch boxes or whatever they are, and they had just random numbers in it. You look at them and they're just random numbers, and but they were the random numbers you had to have DES work. And in the first analysis of DES showed that 8 bits were not used at all. It came out as a 64-bit encryption. It's only 56, right? And then closer analysis showed that a couple of the bits only had a half a bit of interest, so they dropped down another bit just by a couple of the bits are highly correlated or redundant.
Mm-hmm.
And it went on like this. And can you imagine if, for example, that was a real bug? A lot of people still think it's a real security bug. And it was super secret. I mean, the whole idea was that it was the DES, and they kept it a secret how these things were created. I mean, a set of random numbers that you use, you can describe as a set of random numbers, and you give the random number generator that generates it or something. You do something, or you see how it was done, but that was all secret, And then the whole thing was secret in that DES put out a bid for people to supply DES, we want a DES, an encryption standard. Give me yours. And then on the other hand, they caused IBM to actually make the submittal, which they were going to accept. It was done before they put out the bid. And they put the name of NBS up because they're nice bureau standards. They're sweet guys. They'd never make a bad choice. So it was all a hoax in some sense. Mm-hmm. And IBM actually submitted 128-bit standard DES, same similar thing, and that was rejected. Yeah. And they come back with a 64-bit standard, and so. It smelled so bad that all the cryptography people got together, and the magazine kept Cryptologia and things like that. Mm-hmm. It just generated the entire RSA, everything. I mean, that was the genesis of all of these people, finding out what was wrong with DES. And so anyway, during that era and the controversies and all of the smelly stuff that was coming up about that, I was invited to some sort of government thing in D.C. Mm-hmm. And I went down there, and they were just pontificating. They said nothing, and I flew myself down, and I fought for 6 months to submit a voucher for my flight, which was cheaper than if I'd done anything else, And finally, I was invited to version 2 of this thing. And I said, no, I'm out. But then I got a reputation, and there was my critiques of Multics. There were a bunch of security hounds that were big on Multics to supply a operating system for the government to be safe with both internal secret shit and external public stuff, and where you can prove or you believe in some sense that they can never cross. And I always thought that was a bad idea, and I talked about Multics a lot in the like I did here. So.
Yeah.
And so I was invited a lot to a set of security symposium with these guys that were really for it. Ford had a group that were trying to do secure operating systems. UCLA had one, Popek, Rand had one. There were several more. I can't remember them all. But they'd all show up and saying everything was great and wonderful and we should do this. The self-reproducing program that came to my mind at that point. It was years in the past, but it came to mind, and I described it to them, and it's kind of shocking. But anyway, so I never got invited back to most of those because I was just down on it. I says, you don't do this. This is wrong. You can't do this. And so anyway, that's where my security kind of thing went on, and I guess it came from this paper. But before that, at Bell Labs, I was asked to try to break into Bell Labs at very different levels. As an employee, as a total external guy, as some sort of privileged employee. I put on a different hat and tried to break into Bell Labs. And my objective was to find my executive director's salary, right? And they ran their stuff on a totally separate system inside the thing. These IBM synchronous terminals. I don't know what they're called now. They were horrible. But anyway, so I had I had a letter in my file in my executive director's office that said, "I'm contract you to break into Bell Laboratories in case I'm caught with my finger in a jar."
Was it both physical and
Anything,
software?
basically,
Any attack?
The hat, yeah. I had to wear the hat.
Okay.
If I was outside, I had to somehow get in without a badge. Mm-hmm. If I was inside, I had to do it from just walking the halls. If I was privileged, I had to do it from my login on a computer. I had to wear a hat. And at the hat, I tried to do the best thing I could do. And we also, in the Unix room, we used to pick locks a lot and steal things. And do you know the story about? I'll tell you the story. The security department, this means physical security department at Bell Laboratories, have a parking problem. There's thousands of parking places, enough for everybody. But the near ones, people would double park or park in no parking places where loading and stuff like that. And so they went out and got 4 locks. What do you call it? Keys?
The boots.
Boots, the word, boots. They found 4 boots. They bought 4 boots, and they started putting them on cars. But, the guards didn't know how to put them on. And they put them around the brake line, so if you ever tried to leave with them, they'd rip your brakes out. Little things like that. And so one of the secretaries came in, forgot something, came in and ran upstairs to get something, ran downstairs, was not more than 2 minutes, right? And went out, and her car, illegally parked, was booted, right at the entrance door. And so she came up, and we went down there and we picked the lock and stole the boot. And after that, slowly we picked up all 4 boots. And we hid them under the raised floor of the Unix room, right? And the head of security came around and pleaded with us, we won't pick on your secretaries if you give us back our boots. So we gave them the 4 boots. And
Have you continued with that security interest at all?
I've been retired. I haven't done anything. But I was tasked in Google while I was working there as a real employee as opposed to a virtual employee now, with reading the phone thing, the half of the phone that the Android.
Okay.
And for security purposes. And I found some things, and I didn't. But I thought it was a bad idea because they split the DSP into 2 halves, and one half runs the phones, the wire, the waves, in a way that that makes you can't just destroy everything around you, right? And one runs the phone system, but it has all the the Wi-Fi and all that crap on it. And I thought that it could never be bug-free. And it was asking to be hacked where somebody would own all the phones in the world, And so I found a couple of specific problems, but by and large, it was very well done. But I said I don't like it just because of the potential. It's just too scary. Maybe I'm just too conservative or something. Anyway, they were in a position, and they were right, that they got to do it or they're going to be out of the market, right?
Right.
And they had to do it. They did it. So but there are more phone systems like that, and God, they got to be careful. It's so hard to write something correctly.
Yeah, it's daunting. Well, if I could, I wanted to, I kind of wanted to talk to you a little bit about chess now, if that would be okay.
Sure.
You talked a lot about your history with chess in the previous interview for the Computer History Museum, but there were just a couple of things that I wanted to touch on for this interview, if I could. And one was, just how early on you wrote a chess program for Unix.
I wrote it. There was the early ACM at their major conference every year had on the side computer chess tournament. And there was a group of people that would organize it. Monty Newborn was the major one. He was a professor in Columbia at the time. And I read about it. I'm not sure how I learned about it. Probably going to an ACM tournament. But I called him up and said, I got some ideas on chess. What should I do? He said, write a program, submit it. And so I wrote a program, and then we played each other by phone from Columbia to Bell Labs. And then I took it to the ACM. So that was the year, probably 72.
Okay.
I think it was the 73 tournament that I first competed in. It was a pure software program. And I came middle of the pack, middle of the road, exactly middle. And then at some point I brought it back, and when I was doing the end game stuff, the table-based stuff, I found a piece of hardware that I would like to build that would speed up this conversion from position number to actual position, back and forth. And so I scribbled down this piece of hardware, and Joe Condon actually built it for me. And then after a while, I figured, well, I can actually use this for chess. So I wrote a software-hardware combination chess machine and it was in the 78 tournament, ACM tournament, and won flat, 4 out of 4, and beat the champion and beat the next 3 people actually. And then I took it to Toronto, and the same thing in Toronto in 79, and came in second. And this time, Joe Osana was all enthused about this. Not Joe Osana. Joe Condon was all enthused about this, and so we built a really massive piece of hardware. I mean, it was almost a joke how big this thing was, and we took it out for 80. And 80, every 4th year, the ACM tournament was called the World Chess Tournament. And what we did, by this time I was in the organizing of it too, and reading, deciding who was going to submit and play and things. And so for the 80 tournament, which is a world tournament, it would be the second world tournament, they decided to have them every 4 years. 3 ACM tournaments and 1 world tournament, 3 and 1. And then the world tournament, in fact, was a dilution of the ACM tournament. All of the top chess programs came out of the United States and Canada. And they were the ones in the ACM tournament. And for the world tournament, we had to throw out a Canadian and bring in a German, and we'd throw out an American and bring in a Taiwan, you know. And that was in fact a dilution. The world tournament was in fact a dilution. So it stomped in the 80 world tournament. And then it won 6 or 8 times. And then
Throughout the 80s, right?
Throughout the 80s,
Yeah.
yes. And so that's how I got into it. That I wrote a pure software program that never got out. It was distributed with the first Unix, and because it was written in C, and then it was the one that went to Atlanta in '73, and then after that there were hardware combinations.
Well, I wanted to just ask about, there's been this long history of sort of AI research and computer chess. And I wondered how you saw, yourself fitting into that. Were you reading that literature?
Oh, yeah.
Was it a resource for you? Did you see what you were doing as artificial intelligence?
Yes, I read it all and understood it. And basically, what was called AI in those days was where you get together with a master level chess player, and he says, "Look for these patterns," and they just put those patterns in. And they tried to look deeper by not looking at as many things, and it was always a mistake. It was always a mistake. I've never saw one that could last a tournament, much less a game, without playing well and then getting slaughtered. It was just, like I said before, it's never having to say you're sorry if you look at all the possibilities. And computers were expanding at an exponential, and so that they could look at more and more of the chess moves deeper, because that's an exponential. So the combination of the two exponentials mean every 5 years you could look at one more ply, and it got to where they were very good, very, very good. And that version of AI of being narrowing the search never got anywhere near any of the brute force ones. It never came close. And but this is what's going on now today, called AI. Those are two different words, completely different words.
Yes.
Today's AI is a very different animal, and it's very impressive that you can actually do that.
I was also interested that I saw that, Claude Shannon, while he was at Bell Labs, worked on chess. He worked on and had this relay computer for chess and games. I was wondering if you had read that work or if that was an influence on you.
Claude Shannon retired just about the time I got there. And he came in to visit his friends. And I went to visit him because of the alligator, I was friends with his friends, and so I knew him quite well. And we went to, anyway, so back when I was organizing the ACM tournaments, on several occasions we invited Claude Shannon to come to the tournament to be the big guest, right?
Right.
And so, yeah, and in fact, I've got a signed copy of his chess paper. It was 48 or 49, something like that. There was he had an algorithm. He actually wrote a chess program, but it was not with computers, it was with people. And the people were called computers. Do you know the term?
Yeah, for a person performing these calculations.
Yes.
Yeah.
And typically at Bletchley Park. And so I'm sorry, it's Turing had the computers. But so anyway, yeah. I mixed up the two things,
Yeah.
and I apologize. So I go ahead and ask your question. I'll try to answer it really.
No,
real.
it was just. So did Shannon's interest in endgames? Did that relate
I'll be honest,
at all
I
to
didn't know
your
Shannon
stuff?
did endgames. I didn't know he did a relay computer.
Well, I have, yeah. They have.
But I only know him from his paper, which Shannon Class A and Class B games, and his he basically invented information theory,
Right.
Little thing on the side. And I knew him. His wife was he was Alzheimer-ish for a large period of his later years, and his wife would bring him out. His wife took him to the World Computer Championship in Linz, Austria, and he was probably at his last, what you would call a person.
Mm-hmm.
Do you understand? I don't want to be
Yeah, I know what you
derogatory,
mean.
but it's such a
No,
horrible
I know
disease.
what you mean. Yeah.
Such a horrible disease. And his wife brought him around and got him to the places he was supposed to be, and that kind of stuff. And then after that, he was just too far gone to do anything.
Well, I wanted to talk about another one of your research interests at Bell Labs connected to artificial intelligence, which is voice recognition. Did you work on voice recognition?
Not at all. No.
Oh, I thought I had read somewhere that you did. I guess
No, not at all.
I guess I was mistaken. Sorry. Well,
We did voice synthesis.
maybe that's where I got confused.
Yeah.
Well, one thing I wanted to also ask about is, in particular in the early part of the time, your time at Bell Labs, there was a lot of exciting work being done, I think primarily in Max Matthews' group, of bringing in artists into Bell Labs.
You're talking about Schwartz?
Lillian Schwartz, but also
Lillian and I we lived, 6-8 houses from each other in Watchung, and she built Spock's brain. In Star Trek, there was an episode where they extracted Spock's brain to run an alien city, right? And of course, Captain Kirk goes in to try to get the brain back, right? And the brain was this plywood model thing, and every Thanksgiving, every Halloween, Lillian, who built the brain for Star Trek, had it in her living room and invite all the kids in to play with Spock's brain. It was kind of cool. So, and our very good friends, Lillian's husband was a doctor, a pediatrician.
right.
And one of our very, very good friends had a group of kids, all of which were, and we talked and went through that. And she was at work, and she and I did a lot of collaborations. Did you see the? It was much to do about nothing, but basically it was a portrait of Leonardo da Vinci on one side and Mona Lisa on the other side.
Yes.
That was Schwartz. And when she was doing that, she had heard that there was a charcoal, what do you call it, a
Preliminary sketch.
preliminary sketch of Mona at a little tiny museum up in I even forget the name of the town. It's like a 2-bit town next to Albany, upstate New York. And so she talked me into flying her up there. We flew up there and we went to the place. We saw the sketch and saw this, and it's very Mono-like. It could very well be, and it's holding a frond, a big, with fuzzy, and the real Mona doesn't have that. It's the only difference in it, and so she goes back and starts researching fronds and what they mean and this like that, and she comes to the idea that this might be, self-portrait, and so then she does that. So anyway, that was my connection there. Plus, there was a guy who was left Bell Laboratories maybe 2 or 3 years after I got there, named Ken Knowlton.
Yeah.
Who lived next to Bonnie.
Okay.
Bonnie was a kid, and Knowlton was doing these shaded things with little symbols that were different colors and things like that. And he also had a language called Explore, EXPLOR. And his Explore language wasn't exactly interactive. Basically, you'd type your program on cards, you'd submit the cards to the deck. They would generate a magnetic tape, which you would take to a microfilm tape player. It would read the magnetic tape, and then a day later, you'd get 35 millimeter frames, single frames, after they exposed them, developed them, washed them, and printed them, right? So it wasn't exactly interactive. So I wrote an interactive Explorer. It was Knowlton's Explorer word for, it was the same. But you type it in on a terminal and it just comes up on a screen, right? A little bit faster. And Lillian was very into Explorer and was playing with it and getting probably most of the stuff, and then she adopted me when I had one that she could just do, and so that was my other interaction with her, was through Explorer. And another one, I wrote a program. Do you know Conway's Life?
Yeah.
There's a torpedo. It's a 5-place thing that goes like this, right? It goes off at a 45, or and anyway, she fell in love with torpedoes, and would take close-up movies. She was like movie buff, made movies, and she'd take screens that were so uptight, so close that you could see the blur on the cathode ray tube on the thing, as this Explorer thing would go by. And she did some of her MoMA work with that.
I've seen that imagery in her films.
Okay.
Yeah.
So she put a lot of Explorer imagery and a lot of Life. The Life was mine, and Explorer was Knowlton's. And she lived close, and we were friends until we left. I love Bell Labs could actually go out and hire somebody like that. What would you like? Oh, I'd like an artist. You're a computer company. No, we want an artist.
Well, I know you've talked extensively about in a recent lecture about your involvement with digital music and the digital encoding of sound and the PAC format and the list, the player piano. I wondered if, there was anything. Well, one, I was wondering, was that work taking place was that across the 1980s that you were doing that primarily, or when was that real bulk of that work taking place?
The PAC and the encoding was in the early 80s. That's where we talked about the golden years in Munich. And in 88, I took an inverse sabbatical. I left work to go to teach, right? in Sydney. And there I actually gave some talks on PAC and made a what you call a Walkman, but it would these hard floppy disks, the little 1.55 megabyte health. You'd plug it in and it'll play a song and then spit it out, And I took that around and the idea was so great, and so it was a Pac-Man, it was a Walkman, but we called it Pac-Man. And then when I came back, I thought I started collecting music. So it was post '88. It was very early '89, end of '88, beginning of '89, that I started collecting music, and that continued until several years ago, maybe 10 years ago, when the internet would get you every song you ever wanted, so that there was no collecting anymore.
Right.
It was hard in the beginning.
Yeah. Well, I wanted to talk a bit about Plan 9 and how that project came, started to gel, how that came about, and what the real motivations behind it was.
I loved Plan 9. I mean, I think it's the best operating system out, except that it doesn't have the apps everybody demands. So it'll never make it, ever. And the major reason it didn't have a browser. Without a browser during the era when everyone went to the internet, it's over, right? So, but the operating system is clean, precise, pretty, very capable of doing anything. It's just really it's actually a great operating system. And it was mostly Rob Pike who did it and designed it. And it had some ideas that were just still way beyond the time. One is we wanted multiple machines to connect together, and we wanted them all to run Plan 9 and to communicate as though they were next door or far away or whatever they are. And we, at that time, we didn't have fast lines to work, but we all had graphical terminals, which needed flat, not fast by today's standard, but fast by those standards. And so the idea was to build, they were independent of Plan 9, but Plan 9 made it work, is that you have a Plan 9 terminal in your home, and it's old technology and old, all you had to do is draw bits on a screen. It had no software, it did nothing. And so it would be an interface on your terminal and your keyboard and your mouse and whatever you had in your house. And Plan 9 would take it and multiplex it and do whatever it wanted, whatever you set up to do with it. And it would transmit at low bit rates because there's no traffic there, right? You draw a screen, which is the highest little tiny burst of traffic, and outside of that, nothing. So to a big computer somewhere else in a central site. And it had no terminals, it had no nothing, it was, and so there were three Plan 9 devices, right? One was the terminal, which was the thing I just described. One was the computer, which was a hierarchy of things in the computer center, fast ones, slow ones, far away ones, and file systems. And the file system, it was all based on a protocol, and the protocol was a multiplex protocol of basically open, close, read, and write.
Mm-hmm.
And one line of the protocol, one multiplex, there was a line and there was a protocol on the line, but there could be multiple protocols on the line. And one protocol on the line simulated what you could think of as a file system.
Okay.
And it would give you a whole hierarchy of file systems. So the line that read the terminal and the mouse would be a file system that had terminal, it had a file called terminal. You read and write bits in there. A file that you call speeds or windows, or something like that, and then a mouse, right? And so if you wanted to do a window system, you see, you would give the entire terminal as one of these interfaces to your terminal to a multiplexer that would make windows out of it and use this one. And so each of these now would be a terminal. And you could run one terminal to one CPU server and one terminal to another CPU terminal. And then the file system was a large multiplexed cached file system, the best you could do. And it was backed by a worm. A worm is a WOR, and write once, read many. And it's basically a CD, a writable CD. And you write it, you can't write it again, it's over, right? And so we had a normal Unix-looking file system that would serve one of these, a multiplex version of this protocol on fast links. And when it boiled down to real files, the real directories, it's not a file, it's a directory now, that it would there was a thing in it called a backup.
Yep.
And you would say, now I want to back it up, and it would create, of your file system, it would create a hard version of your file system that will be dribbled out to worms, so they'll never change. They're permanent, right? And then it would create a new superuser, a root of the whole file system, that had that as its data. And that one, every time you wrote something to a file, it would split it and then keep in disk the file that's been modified, but keep in worm the original.
Oh.
But now when you said split and make the hard disk, make the backup, it would create a backup version of the old one. So, and it would keep a directory of all the ones you've ever done. So it was very economical in space, and it overlapped all files that you had created. The read-only part of all the files were on worms, and the writable parts were in disk, which you could back up any time by just saying backup.
So
and then there was a directory that was created when you said backup, which had the date of every backup. That was the name of that file system. And so it generated a whole bunch of very strange commands. The best one was called yesterday. And you'd say, okay, what you could do very easily, and you did all the time, is you're going to start some new project. You say backup, and then you say, oh shit, that doesn't work, and you bring it back. You go back to where it was, and it was the exact instant that you said backup is the whole file system is still there. And then somebody comes in and says there's a bug, right? And you say, well, it came in last week or the day before, it was, years ago. And you go back and you write a little test program that handles the bug, and you walk up yesterday every file system until you find the one that broke, right? With a test program, you test broken, test broken, test broken, test fix. It was broke in that region. So you then take these two regions and compare all the software that changed between those two regions, and that would almost always give it to you. If you didn't do it, you could do a diff.
Mm-hmm.
You know what I mean?
Yep.
Of of you could either do a diff of just those two, and it would tell you if the other didn't tell you. But the other thing, the actual yesterday command, would you say you'd pick one file, you say yesterday this file,
Yep.
and it would go back and tell you when it was modified and what was modified. It would give you diffs every time it changed in the backup system.
This historical file system, or whatever we want to call that, it's really so interesting. And what I couldn't grasp is how the size of the backups on the worms how come it didn't balloon in size?
It doesn't balloon. It grows exponentially like all file systems. But the people who produces worms also grow exponentially. I'm telling you, it stays. And there's a rule that all file systems are 90% full.
That's certainly true of me.
Okay, and likewise, all worms are 90%. And a lot of worms are expandable. That they will have racks and racks and racks of disks.
Okay.
Whatever you're storing them back on. And if you're getting close to out, you put enough in to be 90% full again, right? And then if you run out of the facility, by that time they have a new one with higher density disks and or what, right? And then with Plan 9, because you can keep a pointer to the old one you just put on the shelf, and the new one, you can have them combined because that's just a file system, which is what, they will go together. If you're doing recent disks, they will point at this file system, and if it'll point at this one, which is obsolete hardware. And so it grew with it anyway.
So is each backup a full copy?
No, just things that modified.
Just the differences.
Just the blocks. If you write 1 byte, it'll
does that block
out of a gigabyte file.
Got it.
All the rest of them are already in the backup.
Right. So it's saving all the changes each time.
Yes.
Okay. That's what I thought was going on. Was that your idea, the historical file system?
Yes.
Okay. And where was that inspired by something in particular? Or?
No, it was inspired with the fact that the way I program, I do massive changes occasionally. And very often I say, damn, that didn't work. And I want to go back. And what I would do now, without that kind of file system, and before, without that kind of file system, I would take whatever I'm thinking of modifying, copy it into a temporary set of directories, files, and then work on the current ones. And then if it was bad, I'd copy them all back.
Right.
Which is it's a strange way, because the stuff you do now touches lots of stuff. It's not just a little tiny set that you can just copy.
Right.
It's like you're mostly here, but then you'll change a library thing or some.
I wanted to ask you one other question about Plan 9, is that Rob Pike said something to me which sounded really important, but I wasn't exactly sure how. I think he said, unless I misunderstood what he's saying, that Plan 9 was all text.
Yeah.
And then that reminded me of, I think, something that Doug wrote about the Unix philosophy or something, that, text streams are the universal interface or something.
That's what pipes are.
So if we have, just these two things, in Unix with text strings as the universal interface, Plan 9 being all text, is there something profound
It really
in
wasn't
there?
all text, but most of the major, if you had some hardware piece of thing like MP3, it'd be MP3 going between them.
Right.
But by and large, like if you were developing like if you're running a terminal, right? there's lots of things. There's baud rate, speed, I think stuff. I mean, they have a bunch.
Characteristics.
Yeah, there are a bunch of things. Or even if you wanted to emulate an old one, or whether you wanted what's the never mind. Anyway, if you had something that was a parameter on the terminal, like the speed, it would be in a separate file in the Plan 9 pipe, the Plan 9 protocol, that would be a separate file called mode or something like that. And if you wanted it to go 9600 baud instead of 110 baud, you'd just write a 9600 9600 into that slot, just with an echo command. Echo 9600 there, and it would change the speed of your terminal. And the ultimate of this kind of thing is that you can actually run the run IP and SSH by echoing IP numbers and addresses and things into the IP driver.
Okay.
So it's very strange you could do that kind of stuff, and but it was very, very handy to have this the text. There was a CD writer. Okay, now CDs are complex in that there's analog, digital, and expandable. You haven't, you can write for a little while and write a track, and write another track tomorrow and another track till you say finalize, right? And so you could plug one of these CDs into your CD reader writer, whatever it's called, and then look at it by LS, right? And tell you what position it is, which of the tracks are analog, which of the tracks are digital, which of the tracks are, and how many tracks are, and how much space is left. It's just the status of the device. And if you want to back up a new analog disc, or you just copy analog PCM, 16-bit PCM to the next track. There'd be track 1, 2, 3, 4, and then next, whatever next, right? And you just copy to that track, and it would write it, and then it'll appear in the status. And then you say finalize, the next would go away. It's a read-only CD. So it just works in every instance, and it becomes just easy to do things like that. Everything becomes way simpler.
Is there, and this is a question out of total ignorance, is that kind of approach, all text approach, is that in any of the common operating systems today? I guess.
Not that I know.
Okay.
Some of them, they will interpret some binary thing. Like you can ask the speed of your terminal and it'll say 9600. That's not what it is. And, it's 5 in the hardware or something.
In the Plan 9 project, you guys came up with UTF-8 to solve some problems that you had, which is now, I guess, absolutely predominates how, text is represented, on the web. Could you talk about, what you were doing there?
We heard that and got a paper from someplace in Texas where they were submitting a proposal for a standard to have what they called FSS file safe file system, and that it's a bad name, but anyway, and it never lasted, so it's good. And it was essentially, there were tons of extensions for problems individual people had for bigger file systems. Like there's Latin 1, I ever heard of that? Latin 2, 3, 4, 5, 6. And Cyrillic, which basically taking ASCII, which is 7 bits, using the 8th bit for another 128 characters, and in that you put Cyrillic, so that it makes the Cyrillic people happy, and now the people you don't make happy are the Japanese and the Chinese, and because they want more than 256, they want thousands, and so they used to do these WCHAR, wide characters, and various forms of extensions for them, right? On and on. I mean, and these are proliferating at more than one a week, all these things. And it's a big deal to do that because you got all the characters and all the graphics and all the, it's just a mess. And you got all the software that now is going to be written with those character sets becomes obsolete when they disappear. And so anyway, that's the problem that this was trying to solve is, okay, now another group of people, mostly linguists, gathered together a thing called Unicode. And it is a list of every character by picture in the world. That's their idea, right? And it was supposed to fit in, I forget how many bits, 16 first, and now it's up a little higher. It's around 24. Because they started bringing in, South American, headhunters and Indian tribes and things like that. So, but it was they had a book, and the book was good, and you can find, as an American, you can find any character you would ever use, even if you're talking to Europe and things. Maybe not if you're talking to Seminoles, but and so this safe file system thing was a proposal to have an encoding that wouldn't be onerous on people who were like in Latin, right? It wouldn't be, that Americans use 7 bits, right? And everybody else uses 32 bits, right? That would be wrong. Microsoft came up with a Unicode RAW that was really horrible, and it suffered, and it was just horrible. And somebody else came up with one like that. But so anyway, this actually solved the problem, and we were in a position where we owned the system, we owned everything, we had the full file system, we could go back and modify anything, and we went through, and it was mostly in 7 bits, and 7 bits was the base of all of these systems. We actually overnight, Rob and I, modified, put in this Texas code, right? But it was horrible in computation. You'd have to do a mod, 2 mods and 2 divides for every character, right? I mean, just horrible computations. And it wasn't even easy after that. After you did all that work, it wasn't even easy. And but we did it, and we were happy because it really worked. And if it's going to be a standard, we'd be the first ones to have this standard. We'd be it. We'd be in the driver's seat. And it slowed things down. I mean, you couldn't type as fast. You couldn't type put on the screen text at nearly the speed that you used to. Right? It just was too computational. And there were still CPUs that didn't have a divide instruction, so you'd have to do software divides. So anyway, we did that, and then we heard that there was the standards meeting come, and they were proposing it to the standards meeting, and they heard that we had implemented it, wanted to know if we had any thoughts on this, and we thought that was too slow, and they said, "Well, have you got anything better? We'll think about that." And so in one day, we went down to a dinner at Mom's. I don't know if you know.
No.
There was a joke going around that's you should never eat at a restaurant named Mom's. You should never eat at a restaurant that's above the first floor. You should never eat at a restaurant that rotates. That's on a, you know. Anyway, there were about 5 of these. Never eat it. Never. And so the restaurant that we went to mostly, we called Mom's. Like you're never supposed to eat there.
Yeah.
And we were at the table with napkin, right? And I wrote down the code for this, for
UTF.
Unicode and UTF. And we went in and we changed all the Texas stuff to our stuff in a night. And ran it for like a day or two, and then we submitted it to the standards committee, which was sitting waiting for our reply, and they adopted it instantly.
And it solved that speed problem.
Yes. It's ands and ors instead of divides and mods.
Mm. And
it's extensible. You know, if as Unicode gets bigger and bigger and bigger, you can incorporate nearly any size character set.
well, I wanted to talk with you a little bit about, I mean, gosh, there's so much to talk about in your work after Bell Labs, but I thought maybe we could just sketch out some of that trajectory if we could. You know, I understand that you, along with a lot of other people, left the labs around 2000.
2000, yes.
Because they were offering people.
I was waiting. I've been waiting for 3 years for a buyout, but it never came. So I left with them.
Okay.
Without a buyout.
Oh, really?
Yeah.
And was this just because of the problems happening from the breakup of the Bell system?
Yes, definitely. It had changed. It was really different.
Really
you had
different.
to justify what you were doing, which is way above my pay grade.
Well, at that time, you went to Introsphere, is that?
Yes, we created Introsphere.
Created it. Could you talk, you were there for about 6 years, as I understand it.
Yeah, I think so.
Could you talk about what the company was trying to do?
It was a last mile company, fiber to the homes. It centered around a fiber protocol called it's where you have a single transmitter from the central office and an active laser to do that, and that the splitting was done by mirrors.
Okay.
It was the word I'm thinking for I want is the word for not having anything active in the splitting.
A passive splitter?
No, not passive. Anyway, so you could split it down to 64 at those points. It's better now. 64, you could run 64 homes off of this.
Okay.
And it was a packet-oriented thing, and you'd send a packet to a place. Everybody would get the packet, but only the guy who got it, who wanted it and had his address on it, would get it. Right?
Okay.
Would use it, and then he could send back. Now, the major problem with that is what is a packet and where is it in this list? Because some people are, it was meant to be a max of 20 kilometers away, right? But it could be right next door. And the difference is massive in delay times. So if you send a packet out, this guy sees it, in 500 mics, and the next guy down there sees it in a millisecond. You understand?
Mm-hmm.
Huge differences. And so the key to this protocol is that there's a delay line that's up to 20. Think of it as in time. You can think of it as a time delay line, although it's not. It's a bit delay line that the time is the number of bits, right?
Mm-hmm.
And so the delay line was 20 kilometers long in the thing. And so you talked like you were on the end of the line, 20 kilometers away. And you'll get your answer. If you're right up close, you'd have a huge delay line, and you'd get it at 20 kilometers, and which is synchronous with this pseudo time that you're on the slot. And then you'd answer through the delay line back, and it would come out at your time slot and be transmitted on the line. So everybody had a 20-kilometer delay.
Got it.
Built. And it just ran perfectly. You had to have like only one bit of slop between all the users. That one packet and another packet had one bit in the middle. And you could visualize the packet going doot 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 doot, and the other guy going doot, and they go like boom, like this, They wouldn't touch each other. So it was beautiful. And when you wanted to bring somebody else on, which was a rare event because this is a used protocol by everybody on it, every now and then you would leave a big gap, real 20-kilometer gap, right? And say, anybody want to sign on? And they'd come back, and then you'd measure where they came back in real time, not pseudo time, and then give them a delay line length to operate through. And so anyway, we actually did that. We marketed it. We had a couple of customers, most of the local telephone things, and we were having a bad trouble selling it to the big guys, Pac Bell, these kind of guys. And so we decided to sell out. So we sold to Alcatel, French company anyway.
Yep.
Some French company. Ericsson, sorry. Swedish.
Okay,
We sold to Ericsson. And Ericsson took it, upgraded it once or twice, held it for many years, not many, but a few, and distributed it in Spain, and they were a big deal. Spain and China, Hong Kong, which was a separate place in those days. Yeah. Anyway, they did it, and then they got rid of it, and we had a competitor called Calyx, who's still in existence now, and we thought we killed them, because but they lived and we didn't, and then Ericsson sold to Calyx, and Sea Ranch has a Calyx product to fiber to every one of these homes has fiber to it, and we got a thing, and I talked to Calyx, and they won't talk to me about what the protocol is. They won't say anything, but I go and I look in the box, right? And I swear it's our design.
Oh, really?
Yes.
Oh my gosh, that's amazing. Well, so did you leave around the time of the Ericsson purchase?
Yes, exactly at that time. Basically, the purchase was done.
Okay.
And Ericsson, they were signing contracts. And the Ericsson side of the contract was, there was a huge amount of money. I mean, like $15 million. This is for people. This is not for equipment or anything. This is, paycheck money that will be distributed after 5 years to everybody who was original, who stayed the whole 5 years. If and only if you keep 80% of what they called the important people. And so I resigned just before the signing of that, so I wasn't an important person. Do you understand?
Okay. Oh yeah. So you wouldn't mess things
I wouldn't screw
Yeah.
up the possibility
Yeah.
of that. And so anyway, so it was simultaneous, but not really.
Okay.
Not really.
Because you knew you wouldn't want to stay there for 5 years.
And Google had been after me for, like friends like Rob was there and Posada was there and, all these really good people. The boss who was, the guy who was the head of Intersphere, Bill Corrin, was my director at Bell Labs.
Right.
And there was no CEO while we were developing. It was all development, right? Mm-hmm. And then when it became CEO time, when we had to kind of sell it, right?
Yeah.
There was a discussion whether or not we were selling to be a phone company or whether we were selling to sell out to make money, just walk away with,
Right.
moving up. Corin wanted to make it a phone company. Now wanted to make it work and put our names on it, right? And we discussed it and voted, and we voted to sell out, which became Ericsson. So we got a sellout type of CEO. And Corin got pissed anyway, so he left and went to Google.
Okay.
And became a very high executive at Google. And from that point of the time that we picked up a CEO till the time we actually sold, which was like 2 or 3 years, Corin was moving up in Google, and he was after me. I'd get sometimes weekly, but mostly around monthly. You ready to move yet? And here's what we can do for you. All of this stuff. And I'd go in. I was good friends with Eric Schmidt, who was
He had been at Bell Labs, right?
He'd been at Bell Labs, and I'd go into I get tours of Bell Labs, and I'd go. It was kind of funny. I'd go to Rob Pike's room, and I'd say, "What you doing? I can't tell you. It's secret. Come on, don't tell me." And I'd walk by Eric Schmidt's office. He's come in here. He's like, "You know what we've been doing?" And that was very funny. So anyway, when they heard we were selling, and there was a time limit, I mean, basically, they kind of assumed I wasn't going to become an Ericsson employee. I wasn't going to go into another phone company. They intensified the thing, and we started getting swag. I mean, it was, you can't imagine. Do you know what an American Flyer is? It's a
sled?
No, it's a
wagon.
Red wagon. We got American Flyer full of swag, with candy and Coke and flashy laser kind of things and badges and shirts and it was a full American Flyer full of swag. It had a gumball machine in it, and they were just plummeting. And then they gave me offers that as long as I was leaving, I mean, that's the place to go because it was an exceedingly good offer.
And could we just talk for a little bit about? I mean, again, there's probably tons of stuff to talk about your time at Google, but I mean, the creation of the Go language, which has become such an important programming language for, let's just say, cloud computing. Could you talk about, what was the impetus for that, and what were you trying to do with that language?
Can I tell you an unknown story before that one?
Please.
A Google unknown story.
Please.
And it may have to be edited.
Sure.
All right. So there was a project when I went into Google that I learned about Google. It's called Google Books. Now, there is a Google Books now, but it's not the same. It's the remnant of the same, but it's not the same. And Google had a plan to make every book available in the world online, right? And they built the hardware and the software to do it, and the disk storage, everything. I mean, it was all done. They took a rack from a data center. The data centers were racks.
Yep.
Of flat computers about this high, and then there was disks in the middle, and then computers below. And they took a rack out of a data center, right? I didn't take it; I just built another one, and put it on some sort of portable carting kind of thing, and then they built a reader, an OCR reader, that would mechanically hold books at a 90-degree angle, and then a camera here and a camera here. And it would move, and there was a processing that goes on that they'd read this one, right, and display one 2 times ago. And so there was an operator that would be looking at 2 times ago. and would fix it somehow if there was a thumb in the way or something bad. Would go back and do it. And then it would go through, and then they took these, they made several of them, I think on the order of, I don't know, I won't even say how many, but, and take them to major libraries, I mean like major libraries, and go through every book in the whole library at least once, mostly twice, and compare the different ones. And they didn't stop at editions. I mean, they do all editions. I'm talking about every book. And so it might be a book that has 5 editions and 3 copies. There'd be 15 of those things, and go on. So now you understand that it's a big deal, and it's a goal. It's a real honest goal to make every book available. Period. And the modern books, were all being digital, and they had contracts with every one of the modern book producers that they'd get the digital copy, so there was none of this manual stuff. And then they went overseas. They got all the literally all the big libraries, right? And they were just about done. They were, and it was really cool to see this stuff. Oh, it was so great. And then they'd actually okayed it with various forms, with copyrights and things like that, and made the so-called legal notice that you have to make. There's these legal papers where it's just a bunch of things saying I'm not responsible for my wife's debts anymore. Those kind of things. Where you have to announce something, right? And they went to every legal. I saw the budget for just the legal notices. It was, I won't even tell you. So saying that from now on we're going to do this project, and it's going to make every book available. And do you know what ASCAP and BMI are?
Yeah, they're these rights management agencies. Right. Yeah,
and they set up an independent. They didn't want to be told that they're stealing all the books in the world. They set up an ASCAP-like thing, and we're selling shares in it, and we're inviting all the big companies to buy into ASCAP. I'll call it ASCAP. That's not the word. And so they an arm's length. They weren't going to control it at all, right? So it goes on like this, and then they go on, and then suddenly you get. Now this is where it gets kind of tricky. They get a complaint from some minor author in France about some unknown work, right? Saying, I have a copyright on this, and I don't want you to steal my copyright, right? And so it turns into a lawsuit, and another one shows up, and another one shows up, and another one shows up, and it becomes such a hassle. And it turns out now that some major U.S. manufacturing company has paid every one of these people to make this lawsuit, and it brought the whole thing down.
A publisher?
No.
Oh.
Somebody who would like to have that corpus of work in their own building.
System.
Yeah. And it destroyed it. It was gone. And I was into it, and I helped, and I worked hard on it, and it was my first project in Google, and I believed in it. I thought it was the best thing ever done. You could just go on a computer and read any book, literally any book, and so what it turned out to be that they made a date, which is 100 years, I think, where all copyrights in all places are gone, and that even if the owner of the copyright had died and gave it to his daughter or gave it to, that it was gone, that the copyrights were gone. And they now, Google, will give you their corpus, let you get at their corpus 100 years back.
Okay,
before that.
Yeah.
With some sort of, I don't know, empirical guarantee that it's out of copyright by now, right? But everything forward to that, and they just haven't got the time or the effort or the desire to chase down any copyright in the last 100 years for for writes. It's so much easier just to, and that's the way it is now. But if you type in something strange from a new book, right? A new meaning, 100 years, it will give you a little piece of it, and with a quote in it, right? If you quote it right, and then if you go in, they'll say, sorry, that book's out of print, or something like that, whatever it is, right? But they got the data.
Yeah. Yeah.
And so what you can do is look at the beginning of the quote and type it, and it will give you that as the middle, right? And the beginning of that'll give you that, and the beginning of that.
Yeah.
So anyway, you could. I didn't do it, but you could write a program that would suck a book. But I suspect that they know that too, and would prevent it somehow. That you couldn't ask for more than a couple of clippets from the same book, and they might give you some other books besides. So anyway, that's
was that a couple years effort for you, or
yeah.
Okay.
And then I worked on Android for a little bit.
We
on
talked
security.
about that.
And then the way Go came about is that I went to a talk at Google, and it was the Google representative for the ANSI standard for C++. And he'd just come back from a standards meeting and described the new stuff. And the new stuff, in my opinion, was bigger than the language, right? And it was, I didn't understand most of it. It was forms of pointers that meant some other thing besides pointer. It's the data, but it had notions on the data or something. I tell you, I didn't understand it. And it goes on and on and on. And it was an hour talk that was dense on just the improvements, so-called improvements to C++. And some of my friends, like Griesemer and Pike, were complaining about, in Google, there's one repository of source, and you can reference it by library from any source that you go in. So you can write a 10-line program and have a 5 million line compilation on your hands, right? And more than that, that some of these things, like the simplest libc or something like that, library, will be loaded and examined hundreds of thousands of times.
Wow.
So you'd have gigalines of codes coming in on every compilation. Now a lot of that was attacked and fixed, where they would keep track. The compiler would keep track of what was seen and just not open it or look at it. Right? It was like a cache version of, don't look at this. You've already seen it. And for all the libraries that have these so-called if-defs at the beginning to keep it from being done twice, but it would call on them hundreds of thousands. I mean, the staggering. And then they had a big chunk of the Google Data Center. They had hundreds of CPUs doing a compilation for you, right? And then now things just got worse and worse and worse, and those were getting large. You'd wait 15 minutes with 100 computers, compiling a 10-line program, and so that was Rob's big. But Rob was much more into Google software than I was. And that was Rob's big. That it was just horribly complex as it was, and so the three of us got in an office and said, what are we going to do about it? I said, let's write a language. So we wrote a language, and that was it. And it was a very good combination of Rob understood the problems at Google. I'd had language and compilations history, and Griesemer was a Swiss jack of all languages. He knew every piece of every language theoretically, in existence. It was just a good combination. And he'd say, "Oh, that's like some obscure language, and have to run off and try to find a manual for it and see what it was like." And so we built this language with the idea that we all had to agree on features. That no feature went in because I want that feature. That's not good enough.
Mm-hmm.
And it came out nice and clean. And then I left. It was basically a very good language when I left, but it was unknown and unused. And then it went open source, and a huge open source community picked it up and loved it and went through it. And then at Google, again after I left, some of the follow-on guys wrote a set of libraries that are just great. They're just magnificent. And now I write in Google and Go almost exclusively, and almost exclusively I use nothing but the standard libraries for anything. They're great. They're just good.
So it works both for doing this, writing programs for these huge, large-scale distributed environments, and also for something much more local that you're working on.
Yes.
It has that flexibility.
Yes, it does. It's very much like C. C does it.
Okay. And is there a key difference that you see?
The key difference is that it's simple. Anybody can learn it in an hour. There's websites that, and by the end you think you know it. You then may have to go back to reference manuals to get it exact. And there's a window that comes up, which is your version of a terminal with CL running, and you type it, and it's fast enough that you type a program, and as you're typing it, it's running it and gives you the answer.
Wow.
And so when you're done, the answer is sitting down here that you asked for, right? So anyway, I love the language. I really do. I think the Plan 9 and Go would be such a combination. It would just be outstanding if you could put a browser on it.
I mean, that doesn't sound like an insurmountable.
Well, probably not. But anyway, they've gone on, and now there's a really big mega lines of GitHub, and I pulled a couple of those out and used them. There's an astronomy one that I use, and there's a VLC. A VLC.
Oh, the media players?
Yeah, VLC runs off a library, and the library is called VLC Lib, and there's a Go interface to VLC Lib, so that you can do anything you can do in VLC from a Go program, and that's one I use a lot. And anyway, it's just. But other than that, everything, all the chess stuff is in just the standard library. It's the big difference in Go is that it's you handle the data. The data is you actually construct what the data is. It doesn't move things around. It doesn't play with things for you, and it doesn't throw things away. It doesn't add things. Your data structures are your data structures. It's safe. They're completely safe. There's a notion of local and global. There's not an intermediate or a hybrid notion. There's it's garbage collected. Big deal. Big deal. Never worry about that. There's no thing in space. And it's got about 4 really nice new notions, and all of that's been seen before. Everybody's done that in different forms, not together. And but it's got like the constants, right? Everybody else has a constant, which is some form of a piece of data that's in the language. Our constants are in a different realm, and they're maintained in arbitrary precision. Okay, and if you use it in if you add 1 to something, it will reduce it and make sure that it's a 1, and add it. So that it's independent whether you're adding 1 to a floating point or a double precision or a multi-precision things. So the constants are, and it'll do. Somebody did something they showed me. It was, do you know what a Hamiltonian is? It's
Yes.
Okay. Someone solved a Hamiltonian, which is very hard to solve, or invert is the word. Hamiltonian, and they did it in the constant.
Wow.
and it would take longer and longer and longer to come down with diagonal 1s, and then longer and longer diagonal 1s. And because they did it with, a constant plus a constant is a constant of the in the constant realm, and so they got the whole Hamiltonian inversion as a constant, and then they.
Well, I think just in being aware of the time, I think maybe we should end there, unless there's something that you really would like to additionally share.
No.
Well, thank you so much for doing this, Ken. It's been amazing. So thank you very much.
No, thank you for coming.
Yeah.